That'll turn on.
And then an internet.
Thomas, can you hear us?
That would be good. So that's, can people hear me? Okay, good, perfect. Online, okay, whatever. Okay. What about in the auditorium?
We can hear you. Can you
Okay.
hear us?
Yeah, that's perfect. Great.
Great.
Perfect. The slide sharing I can't, while the others, there's a slide shared right now, so that's why I can't really test the slide sharing. I don't know if we can.
Could we briefly stop sharing this slide so that Thomas can practice sharing?
I'm not sure. Perfect. Try. Okay, just to make sure that people can see my slides and as they go through.
Yeah. Yep, we see your slides and we can hear you clearly.
That's awesome. Okay, and it goes through too, right? When I change slides.
Yep.
Okay, perfect. Awesome. Then I stop. Perfect. Thank you very much for allowing me to test it. Makes it probably easier later. Thank you.
Yes, glad to check that everything is working.
Thank you.
Okay, good morning, everyone. Welcome to the first session of today. Can we get Jonathan's slides up on the screen? So our first speaker today is John Gare, who's going to give us an introduction to LISA.
Thank you, and thanks to the organizers for inviting me to give this talk. So I'm going to be telling you about LISA, and this is a good year to be giving this talk because in January, LISA was officially adopted by the European Space Agency as a mission. Adoption was expected, but it makes LISA now a secure mission and leads to a significant increase in funding, both from ESA and NASA and from the European member states. And there'll also be, as a result of adoption, a formalization of various aspects of the organization of how hardware and data analysis is organized and delivered. The LISA mission that was adopted will be very familiar to anybody who's been to a talk about LISA in the past 20 years, because the design has not evolved very much. It will consist of 3 satellites. These will be in free fall, approximately at the corners of an equilateral triangle with sides of length 2.5 million kilometers. You can't find orbits that keep the satellite constellation exactly equilateral. The arm lengths fluctuate by about 2% over the course of a year. Along each arm of the interferometer, there will be 2 laser links, one going in each direction, and it's these laser links that will be used to measure the light travel time along the arms, and its differences in the light travel times between the different arms of the interferometer that encodes the information about the gravitational wave signals that are passing through the detector. The constellation will be in a heliocentric orbit trailing the Earth, and it'll be gradually drifting away from the Earth. At the start of scientific data taking, it'll be about 50 million kilometers away, and over the course of 10 years, it will drift to about 70 million kilometers away. It's an ESA-led mission, but NASA is involved as a significant junior partner, providing both hardware contributions and contributions to the ground segment, which is the data analysis. And one of the reasons that we were able to get LISA adopted this year is that a lot of the technology has now been proven, mostly as a result of the LISA Pathfinder demonstration mission that was launched in 2015 and was spectacularly successful. So why do we build LISA? Well, we're building LISA to fill a gap in our gravitational wave frequency coverage. The ground-based detectors, LIGO, Virgo, CAGRA, operate in the audio band between 10 hertz and kilohertz or so. And we're also now starting to detect gravitational wave background at nanohertz frequencies with pulsar timing. But there are 6 decades of frequency between the two, and LISA will attempt to fill 3 of these operating in the millihertz band. This band is expected to be rich in sources. This plot here shows a subset of the sources present in a single realization of the LISA data. And I'll say a little bit about these various source types over the next few minutes. So just like LIGO is observing mergers between black holes formed from stars, we expect LISA to observe gravitational waves from black hole binaries, but at a different mass scale. It's operating at a frequency that is about 100,000 times lower. That means the typical size of the systems it's sensitive to is 100,000 times bigger. And so we're talking about systems with masses of about 1 million solar masses, but ranging from 10 to the 4 to 10 to the 7 or so. We know that black holes with these masses reside in the centers of galaxies, and we expect that when galaxies merge, the black holes that were in the centers of those galaxies prior to the merger will sink to the center of the remnant and form a binary that then eventually inspirals and merges through gravitational wave emission. These events can be seen by LISA with a very high signal-noise ratio, pretty much anywhere in the universe. These blue contours on this left-hand diagram are contours of constant signal-to-noise ratio in mass redshift space. And we see that at redshifts of 1 or so, we can detect systems with signal-noise ratios of thousands. And even at redshift 10, we have signal-noise ratios between tens and hundreds. The These purple contours here and these red dots show black holes that are either will be observed electromagnetically with JWST, and these red dots correspond to the highest redshift quasars currently known today. And we see that LISA is filling in a part of this mass redshift spectrum that is not easy to observe electromagnetically. And this will help us to understand how black holes have formed and evolve. And the right-hand diagram shows an example of this. These are red and blue curves correspond to two different models for the formation and assembly of structure and show the differences in the predictions they make for the systems that LISA will observe. The number of binaries LISA will see is somewhat uncertain, but is expected to be between a few and as many as 100 per year. And yeah, that the number also encodes information about the massive black hole population. So LISA will be able to measure the parameters of these systems with very high precision. The first table here shows typical measurement accuracies at a redshift of 2, where we can measure individual masses and spins to sub% level and distances to order of a percent. The measurement uncertainties at higher redshift are worse, but they're still order of 10 or a few tens of percent. This will allow us to discover seed black holes in the very early universe and study the mergers of massive black holes over cosmic history, which will help us learn about the growth of massive black holes. There's also the prospect of detecting electromagnetic counterparts to massive black hole mergers, and this will be facilitated by LISA's ability to localize the sources on the sky. And we expect to be localizing events to order of a square degree at merger, and we can, in principle, particularly for lower mass sources, resolve the sky location to a few square degrees or a few tens of square degrees sufficiently before merger that we can send out pre-alerts for EM follow-up. Massive black holes are also expected to be seen in a different type of gravitational wave source called an extreme mass ratio inspiral. These are the inspirals of compact objects into massive black holes in the centers of galaxies. We expect these to occur because galactic central black holes are typically surrounded by clusters of stars. And the stars form compact objects, and the compact objects will sink to the center of the cluster through diffusive processes and can get captured onto orbits that eventually lead them to inspiral and fall into the central black hole. These are interesting sources because the orbits are expected to be rich in structure. We expect the systems to still have a significant residual eccentricity when they're in the LISA band and also be inclined to the orbital plane of the black hole. And that gives them a very rich structure, a combination of multiple different precessional frequencies. And this encodes a lot of information about the central black hole and its astrophysical properties. MRIs will also be observed for a very long time. The inspiral, because the small object is much less massive than the big object, it takes a long time for it to fall into the massive black hole. And we will typically expect to observe each individual MRI for at least the order of 1 year and detect 100,000 waveform cycles from it. This allows you to measure the parameters of the MRIs to even higher precision than we can measure the parameters of supermassive black hole systems. Intrinsic parameters like masses and spins, eccentricities, can be measured to parts of 10 to the 5 or even smaller. Sky location is a few square degrees and distances typically a few percent. And this precision comes from the ability to track the phase evolution of the gravitational wave over the 100,000 waveform cycles we observe in a year of observation. So the MRI systems we'll observe will fill out our information about massive black holes because they'll be probing massive black holes at lower redshift that are not undergoing mergers. So it's a slightly different population to the massive black hole binaries. But we'll measure masses and spins of those black holes with high precision, and we'll learn again more about the massive black hole population. The other thing they will allow is studying the immediate environment of these black holes, because Well, partly we will learn things from the distribution of eccentricities and masses of the objects that are falling into the black holes, but we can also directly see the effects of astrophysical, environmental contributions in the signals. This is an example from a recent paper by one of my students, Lorenzo Sperry, where he looked at the imprint of an accretion disk on the inspiral phasing of an extreme mass ratio wind spiral and showed that you can measure, with reasonable assumptions about the density of the disk, you can measure the effect of the disk on the change it had in the inspiral phasing of the extreme mass ratio wind spirals. The third type of black hole source we could see with LISA are the same black hole binaries that we're seeing with LIGO, which are binaries of stellar origin black holes. So this was realized as soon as LIGO started seeing events, because GW150914 would have been visible by LISA with reasonable signal-to-noise ratio 5 years before it was observed merging in LIGO. So if we do see more of these systems, then LISA, the combination of the multiband observation with LISA and LIGO can tell us a lot more about the system than we can do with one on its own. In particular, LISA can localize the sky location to less than a square degree and predict the time of coalescence to a few seconds, years in advance of the LIGO event, which will be important for looking for multi-messenger signatures. LISA can also measure the eccentricity of these systems long before merger, and that encodes information about formation channels, which you can't easily get from LIGO alone. The one problem with this source type is the number of events is highly uncertain, and as time goes on, it seems to be going down. The GW150914 is still the only event that LIGO has seen, which we would definitely have seen with LISA. But the number we see will depend somewhat critically on how well the instrument performs in terms of sensitivity at higher frequencies. The current design is a bit worse than we expect will be achievable. So if we can reduce this noise at high frequency by a factor of a few, will significantly increase the number of events. But current predictions based on the design sensitivity for LISA say that we might have a few events in total with sufficient signal-to-noise ratio that we can identify them and do science with them. The most numerous source that LISA will see are ultra-compact binaries in our own galaxy. So these are typically white dwarf binaries, white dwarf neutron star binaries, neutron star binaries, and so on. Any binary in the Milky Way that has a period close to 1 hour is radiating gravitational waves in the LISA band, and there are order of 10 million of these systems. We won't resolve all of them, but we expect to resolve maybe 10,000 or so individual binaries. Some of these are already known from other surveys, including Gaia has added quite a few to this list. But we also, the vast majority of them are currently unknown white dwarf binaries. We'll localize them on the sky reasonably well, and also in distance for approximately 10% or a bit more of the binaries. And we can measure frequency derivatives for maybe a third of them, and second frequency derivatives for a few. And this encodes information about tidal effects in the binaries and mass transfer. This is a realization taken from the LISA Red Book, which is basically the LISA science case as submitted at adoption that shows a realization of the galaxy with these green stars. These are all the known galactic binaries that LISA should be able to detect. And then all of these yellow, pink, and blue points are other binaries that were in a particular realization of the galaxy that will be individually resolved with LISA. So you see there are many of these, and this will give us a lot of information about binaries in our galaxy, which will tell us about stellar evolution. And interesting. We'll also, from the locations of these objects in space, we will measure the distribution of mass in the Milky Way. And for systems where we can measure the frequency derivative, or even the second frequency derivative, we'll learn about the interplay between gravitational waves and tidal dissipation in these systems. So the final source type for LISA are cosmological sources. All gravitational wave detectors, in principle, could observe gravitational waves from from processes occurring in the early universe. For LISA, the millihertz frequency range corresponds to processes that occur at the TeV scale in the early universe. This is an interesting scale because it corresponds to the electroweak phase transition. And there are a number of models that people have come up with that predict significant backgrounds for LISA in this frequency range. And then there are also the possibility of producing backgrounds at any frequency, and in particular in the LISA band, from networks of cosmic strings. So a number of these backgrounds were highlighted in the science case, and they're shown by these colored lines on this plot relative to the sensitivity of LISA in the different channels you can construct from the data streams. We see for some of these, the orange and yellow curves, these are well above the sensitivity curve, which might create a problem for detection of other sources, but these are not predictions that are based on physical models. These are essentially assuming that current upper limits from other experiments are saturated. So this is the most that the cosmic string background could be in orange, and this is the most the primordial black hole contribution could be in yellow. What we would expect to see with LISA is an astrophysically generated foreground from all of the stellar origin black hole binaries that LIGO is observing, because prior to merging in LIGO, they're radiating gravitational waves at lower frequencies, and this produces a background, the amplitude of which and spectral shape of which we can predict from LIGO observations, and that should be detectable with high confidence by LISA. So if we do measure these backgrounds, then we can characterize the astrophysical stochastic background and learn about or set upper limits on physical processes happening in the early universe. If we do detect a background with high significance, then we can start to measure its anisotropy. That will tell us both about its origin and about the physics that's producing it. So that's all of the sources that we expect to see with LISA. And I've said a little bit as I've gone along about the astrophysical applications of those observations. I'm going to spend the rest of my time talking about the other aspect of LISA science, which is fundamental physics. So the idea here is that we want to use gravitational wave observations to test the theory of general relativity. Why do we want to do that? Well, we know that at some level, GR and quantum mechanics are incompatible. If you consider systems that are at a scale where both theories should apply, they make different predictions, and so we need something must break and needs to be corrected. So this typical scale is the Planck scale, so that's well below anything we would, well above anything we will observe with LISA. But when you attempt to construct a quantum theory of gravity, this typically introduces infinities which need to be regularized, and this process of regularization introduces corrections to the action, which typically scale like powers of the curvature. So the Einstein-Hilbert action has one curvature term. As you quantize gravity, you tend to get quadratic curvature terms and then cubic and so on. Now, gravitational wave observations can probe systems that have higher curvature strength and field strength than anything that can be probed in other ways, which is why gravitational wave sources are a good system to use to try and identify small deviations from GR that might help us understand how to unify gravity and quantum mechanics in the long term. So there are many different ways you can use gravitational wave observations to probe fundamental physics. I won't have time to go through all of them, but I'm going to highlight a few for which LISA is particularly good. So one of these is to probe the nature of black holes. Black holes in general relativity are described by the Kerr metric, which depends on just two parameters, a mass and a spin or angular momentum. All the other higher multipole moments of the gravitational field are determined from the mass and the spin. And so if you can measure directly those multiple moments, you can do a consistency check to make sure that the object is a Kerr black hole. And if it's not, that might be a hint that something is wrong with your theory. So there are two different ways you can measure multipole moments with LISA. One of these is to use massive black hole binary mergers. After the merger, the massive black holes form a single black hole that is distorted, and this distorted black hole then undergoes a process called ring down, where it radiates away all those distortions and settles into a stationary state, where it's described by the Kerr metric again. The radiation that carries away these perturbations takes the form of damped sinusoids, and the frequencies and damping times of this radiation is determined by the mass and spin of the final black hole. And so if you can measure more than one of these quasi-normal modes, you can do consistency checks that the object is indeed a Kerr black hole. Now, LISA is very good for this because it will see massive black hole binaries with very high signal-to-noise ratio, and this will allow us to measure multiple of these quasi-normal modes. So we can do much more stringent tests than you can with LIGO, where typically we can only see one or two ring down modes. So these figures at the bottom of this page are from a recent paper by Alex Tupiana, where he studied LISA's ability to measure multiple ring down modes, and he found that you could measure 7 of them with quite high precision for reasonable assumptions about the signal-to-noise ratio of the events. The other way that you can probe the multipole structure of the space-time with LISA is by directly measuring the multipole moments from the phasing of the object. When I showed the waveforms for extreme mass ratio n-spirals, I said that they had a rich structure, and that structure encodes details about the orbit that the small object is moving on. And if you can decode that orbit, it will tell you about the space-time structure. Now, for a long time, we believed that MREs would be the best of gravitational wave source for doing this. And that is true in the sense that MREs will be able to place the greatest absolute constraint on deviations from the Kerr metric. However, as I mentioned at the start, when you attempt to unify gravity and quantum mechanics, you typically get corrections that scale with curvature. And curvature is scales with the inverse of the mass. And so the black holes that LISA observe actually have much lower curvature than the black holes that LIGO observes. So even though you get this benefit from having 10 to the 5 cycles in an MRE, you are trying to measure an effect that is a factor of 10 to the 5 times smaller. So you don't actually do much better with MREs for this multiple moment measurement than you can with ground-based detectors. However, there are other effects which don't scale in this way. In particular, anything that comes about from the presence of another field outside the black hole, you can do better with LISA. So there are lots of examples of this: boson clouds, dark matter spikes, and non-minimally coupled scalar fields. The idea here is that there is then something else that sets the scale of the size of the effect, and so it can be similar for LISA and LIGO, and then the fact that you observe many more cycles means LISA is much better suited to constraining it. So there's an example here, again by Lorenzo Sperry, where he looked at the case of this scalar field interaction. What happens there is that the scalar field condenses on the black holes, and it leads them to acquire a charge. And this charge is greater for smaller black holes. And so the size of the effect is determined not by the mass of the big black hole, but by the mass of the small black hole. And hence it's similar size in LISA and in LIGO. And then the fact we can observe MREs for hundreds of thousands of waveform cycles allows us to place a very precise measurement on the size of this scalar charge in the black hole, and has placed strong constraints on the presence of these extra fields. I have just a couple of minutes left, but I wanted to mention a few other aspects of fundamental physics tests with LISA. One of these is the ability to measure alternative polarization states. Gravitational waves in GR are tensor polarized, so there's a plus and a cross polarization mode, but in other theories of gravity, there can be up to 4 other states. This figure here is from a still from a movie that Nico Muniz produced, which is very nice. Yeah, so you should ask him to see it if you can. Now, LISA can potentially directly measure these additional polarization states because it's actually much more sensitive to the longitudinal modes at high frequency than it is to tensor modes. Of course, this only helps if those high frequency, if the alternative modes are excited by a comparable amount to the tensor modes, which we don't know. That's theory dependent, but in principle, we could place strong constraints on direct detection of polarization, additional polarization states. Another thing that LISA is very good at is detecting effects that accumulate over propagation. An example of this in some alternative theories of gravity, which break chirality, you can have a difference in propagation speed between gravitational waves that are left and right polarized. And this means that a system that produces both, the waves will gradually come out of phase as they propagate. Now, this is partly degenerate with inclination uncertainties, but LISA can in principle measure this effect. And LISA is very good for doing this because it can see some sources at extremely high redshift. So the further away the source, the longer it has to accumulate a phase difference from a small difference in the propagation speed. In the same way, LISA can place strong constraints on deviations in differences in the speed of propagation of gravity and of electromagnetic radiation. So this is often phrased in terms of saying the mass of the graviton. We have a very strong constraint already from GW 170817, but that source was only at 40 megaparsecs. And LISA will see things, systems at redshift of 10, which will allow us to place orders of magnitude better constraint on this difference in propagation speed. And this will be true even in the 2040s, despite the fact we will expect to do better and better as we observe more and more events with ground-based detectors. Okay, the final thing I wanted to mention was cosmography. So we had a couple of talks about this yesterday. This is the idea that we can use gravitational wave sources as standard sirens to probe the expansion of the universe. So we are already doing this with ground-based detectors, but we can also do it with LISA. And the thing that makes LISA special for this is that it will observe sources at a wide range of redshifts. And by combining the observations of different source types, we can actually break some degeneracies that would otherwise be present. So extreme mass ratio inspirals will typically be observed at lower redshifts of 1 or 2, and massive black hole binaries will typically be observed at redshifts higher than 2 and up to 10. And by this means that the degeneracy between Hubble constant and matter density is different. So by combining the two sets of observations, you can get a much more precise constraint. And we could get to 1% level on the Hubble constant and about 10% on omega matter using only LISA observations over the course of an extended mission. Okay, so I've reached the end of my talk. This summary that LISA is exciting and will do a lot of science in astrophysics, fundamental physics, and cosmography. But I will happy to take any questions.
Great. We have time for a couple minutes of questions, and there's some in the front here.
Thank you very much for your talk. Just for curiosity, I mean, you see, what LISA observes would be a sum or a combination of different signals from different sources with different frequencies and different amplitudes. So I was just curious, what's the approach or technique you will be using for these entangling. I think that would be very difficult.
Yes, so this is one of the key problems in LISA data analysis, is to simultaneously constrain the many thousands of sources that will be in the data. So the approach that people are developing is it's a Bayesian approach that's based on reversible jump, MCMC. So you are attempting to simultaneously fit all the sources at the same time, but you allow for uncertainty in the source number by varying the number of each source type dynamically as you're doing the fit. So this has been demonstrated already by several groups for data sets that contain only the white dwarf binaries and the massive black holes. It has not been extended to extreme mass ratio spirals and so on. That's work in progress. But the most numerous sources are the white dwarf binaries. And so they're the things that cause the greatest problem for this global fit. And that seems to be under control. But it's an active area of research, and certainly we're far from having solved it.
One more question.
Thank you. So my question was, what are the key unknowns in the formation of Emery sources that we're trying to untangle with LISA?
I think the list of key knowns is probably shorter. So the main problem is that it's not so far been possible to consistently simulate a stellar cluster around a black hole. There are both n-body calculations and Fokker-Planck and so on. But what has happened over the years is, as more physics have been included over these simulations, the predictions have fluctuated up and down. Fortunately, they've gone up and down rather than always down. But there are big uncertainties basically in the process of mass segregation. So we expect heavier objects to sink to the center, but that's typically been simulated with populations that only have a small number of discrete masses. Whereas obviously we expect there to be a spectrum of black hole masses in the same way that we're observing a spectrum of masses in LIGO. So exactly how mass segregation works and what this means in terms of which black holes or neutron stars or white dwarfs end up close to the central black hole and form memories is quite uncertain. Another big uncertainty is in what fraction of the sources that begin as Emery is actually successfully in spiral rather than plunging, because in the initial phase, the Emery orbit has an apoapse that's very far from the black hole, where it interacts with stars, and these stellar interactions can perturb the orbit so that it now, on the next time it comes close to the black hole, it ends up plunging. And the relative fraction of plunges to in spirals is also quite uncertain, and that can make big differences to the rates of events, but also to which systems survive. And so there are lots of selection effects in terms of the properties of the black holes and the small objects that will be hard to disentangle when we do population inference. And it also makes it very hard to predict the rates accurately. When I started working on Emery's 20 years ago, the rate range was 1 to 1,000, and it still is. So I think we have to wait for LISA to see, and we hope it's somewhere in the middle.
Thank you.
Great. Okay, for the sake of time, let's move on. So let's thank John again. And if you have more questions, please come up and find him during the coffee break. So our next speaker is Hongwei Ge.
So, good morning, everyone. I'm very proud to have this opportunity to introduce our recent work about the mass transfer physics in binary stars. It's a theoretical work. So, my name is Hongwei Ge. I'm from Yunnan Observatory, and my collaborators are Zhenwei Li, Xuefei Chen, Hailiang Chen, and Christopher Tao. Ron Webbing and Jianwen Han. So from the very beginning, over the last 2 decades, there are many important insights are found, such as people use the type 1a supernova, find the expanding the universe expansion accelerating and leading to the find of the dark matter. People the ground-based gravitational wave detect many open a new window for gravitational wave astronomy, including the find of the first detection in 2015 and the very massive stellar mass black hole, the merger. And also in the last year, many groups found the nanohertz gravitational wave by using the millisecond pulsars. So those important findings has the binary objects are formed through binary star evolution. So compared with the single star evolution, because of the binary interaction, so they change the evolution fate of the single star, and we can see the formation channels of the binary systems are very complicated. So it can form if the progenitor are massive stars, then it can form the stellar mass black holes, plus double black holes, and neutron stars and so on. Or if the progenitor are low mass stars, they can form the double white dwarf systems. So they are the very important sources of the LISA project. They can also form many other different important binary objects, such as the type 1 supernova, X-ray binaries, and so on. So to sum up, so there are 3 basic questions in binary star evolution. Suppose a binary star forms, and at some point the donor overfill its Roche lobe and transfer the mass to its companion. The mass transfer can be stable. Then they form a relatively long of the pure binary system. And if it's unstable, they will enter a common envelope phase and then form either a very compact binary star system or they can merge. So you can see these basic questions determines the evolutionary fate of the binary system. Sorry. Oops. Okay. But people know very little about these questions. So we can see some the observation and the theoretical prediction are not fit very well. If we take example that, for example, the double neutron star systems, by adopting different initial parameter or the physical inputs from binary evolution, the merger rate of the double neutron star could be different by orders magnitude of 2. So yeah. So there are many different approaches to try to solve the binary star evolution problems, like the mass transfer stability and the common envelope evolution. So normally people use the stellar evolution code to simulate the mass transfer process in binary systems, such as using MESA and STARS evolution code. But they are sensitive to the mass transfer boundary conditions. For the simulate the common envelope evolution process, people usually use 3D hydrodynamic simulation code, but the progress are a lot of progress have been made, but they are still facing their challenges, such as they need to simplify or extend more realistic field assumptions, and also they are facing the numerical challenges. It's very hard and very expensive to do the simulations. On the other hand, we focus on the very fast mass transfer process. It's faster than the thermal timescale mass transfer and close to the dynamical timescale mass transfer. In this case, the mass transfer are fast enough, so we can assume the mass transfer process is adiabatic. The heat cannot the entropy profile of the star can be frozen with its mass. So we rewrite the stellar evolution and the structure and the evolution equations. So with this adiabatic mass loss model, we can predict how the donor star's mass responds to the rapid mass transfer process. So traditionally, people define the radius mass exponent. So this parameter can show how the star shrink or expand during the mass transfer process. And then we can compare the donor's response to the Rotary-Lobos response, find the critical mass ratio. Here is an example. It shows how the star's radius shrinks or responds to the mass transfer process, and the gray dash dotted line are how the Rotary-Lobe radius responds. So we can see here is the example show the critical mass ratio. So overall, this is sensitive to the structure of the donor star, such as whether it's a main sequence star or stars on the giant branch. So previous page show one or two example. Here we systematically studied the donor stars with mass from 0.1 solar mass to 100 solar mass, and the stars, the radius generally show how the star on different evolutionary stages. From the bottom, for the zero-age main sequence stars, and then as they evolve, the radius expand generally. So here the contour map show the critical mass ratios. So compared with previous find, there are two important new findings. Like the first one is for massive stars. Massive stars, they tend to be more stable than we expect. So I will show it later, the results, what's the impacts. And then the second part is related to the white dwarf progenitors. So then the work from Temminck and so on, they compared their results with our simulations. We found that the critical mass ratio, the black solid line, and our results, the red dashed line, fits very well for low mass star and intermediate mass stars. Now we have our theoretical predictions. We needed to compare it with the observations. So the first here, I just show very briefly relate to the double black hole mergers, their progenitors. So people thought maybe the combinatorial evolution channel dominated the formation of these stars. But very recently, a series different paper found that maybe the stable mass transfer channel dominate the formation channel of these stars. For example, Nigel and so on, they found the stable mass transfer plays a very important role, and Vanson found that to fit the merge rate of these systems, the critical mass ratio play a very important role, and that's consistent with our results. And Pico, she showed in the first day that it can explain the large mass ratio binary black hole systems. So today we are mainly focused on the double white dwarf systems. So for the white dwarf, the companion of the white dwarf could be other type of stars like helium stars, brown dwarfs, neutron star, black hole, and so on. But for double white dwarf systems, here we show two examples. For a binary system with a very long opto period. So previous people thought they will undergo a common envelope elevation channel, but by using our new results, we predict they will enter different channel, that a stable mass transfer channel, and then a second common evolution channel. Here also show a short opto period binary systems. The similar with the previous this example, they also change their formation channel to first a stable evolution channel and then a common envelope channel. So not only the evolution formation channel changed their mass and the opto period are also different. So after a binary population synthesis study, which use the basic physical input from the binary star evolution, we found that the first Roche-Lobe overflow channel and the second common envelope channel dominate the formation channel of the double white dwarf systems. And for other channels, they can form different white dwarf systems. Then we use our theoretical prediction like the black solid line and compared with the observed double white dwarf systems. For those, they will finally merge in the Hubble time. So those are the red symbols. So we can see that by using by using the new mass ratio stability, the critical mass ratio, they face the observation very well. And not only for the high mass white dwarf mergers, but also it's true for the extreme low mass white dwarf mergers. So the summary, we build an adiabatic mass loss model and try to solve the mass transfer stability questions, and then we systematically study the donors on with different mass and on the whole evolutionary stages, and then we apply it to study many different binary systems, including double white dwarf and so on. Then I'm looking forward to future collaborations, and because both Lisa and other electromagnetic observations will find more white dwarf binary system. Thank you very much.
have time for one quick question.
Thank you. Thanks for a very nice talk. So this is really great work, but I believe you assumed fully conservative mass transfer when picking your, when finding out what the critical mass ratios are. But I expect that in reality, mass transfer leading to common envelopes will be very non-conservative, and there will be very sensitive to the amount of angular momentum lost from the system. So how does that influence the critical mass ratios?
Yeah, thank you very much for your question. Yeah, you are totally right. That's very important. In a real case, the mass transfer process tend to be very non-conserved. But for example, here, actually, the Roche lobe response or the optical period evolution are independent on the response of the donor stars. So here, the dashed line show a conserved case, but we are preparing our very recent work to either fully non-conserved case or like a or other non-conserved case. We can calculate how the Roche lobe radius respond to non-conserved mass transfer, and then we can we have already studied that. So yeah. We found that for non-conserved mass transfer, the critical mass ratio could change a lot. For example, for massive stars, the critical mass ratio could become quite smaller than what we get from the conserved mass transfer. So yeah.
Okay, thank you. For the sake of time, let's move on. So let's thank Hongwei again. Next, we're going to hear from Kelly Gorgi, and it's going to be a recorded talk.
Hi, my name's Kelly Gorgi. I'm a postdoc at Swinburne University of Technology in Osgrath in Melbourne, Australia. So my talk today is about studying neutron star mergers on So studying the gravitational wave signals alone, strictly through general relativity of neutron star mergers, in theory, provides us with an avenue for measuring the luminosity distance. The equation on the right tells us that if we have this luminosity distance information and we have information on the redshift, we have enough ingredients to perform an independent measurement of H naught. However, the picture is a little bit more complicated than this, of course. And the equation on the left tells us that there's a degeneracy that exists for the gravitational wave signal amplitude between cos I, which is the inclination angle or viewing angle of the gravitational wave system, and the luminosity distance. And this degeneracy Should I try presenting live? If it's not working, it seems like my slides weren't changing. Okay, maybe I'll go ahead and share them.
Is this all right? I'm not really getting any feedback from the chat or anything. I'm not sure if this is working. Okay. Seems like it's fine online, but I don't think my slides are showing in the auditorium. All right, I'll stand by.
University of Technology in Osgrath in Melbourne, Australia. So my talk today is about studying neutron star mergers on milliard-second scales, in particular to ultimately do precise measurements of H0. So studying the gravitational wave signals alone, strictly through general relativity of neutron star mergers, in theory provides us with an avenue for measuring the luminosity distance. The equation on the right tells us that if we have this luminosity distance information and we have information on the redshift, we have enough ingredients to perform an independent measurement of H0. However, the picture is a little bit more complicated than this, of course. And the equation on the left tells us that there's a degeneracy that exists for the gravitational wave signal amplitude between cos I, which is the inclination angle or viewing angle of the gravitational wave system, and the luminosity distance. And this degeneracy is going to be an important source of uncertainty when doing these sort of measurements of H0. So for this talk, we're interested in bright sirens. So this means that in theory, we should be able to get the redshift information by detection of the host galaxy, for instance, through identification of the kilonova. But the primary EM component or counterpart of interest for the purpose of this talk is the relativistic jet. So this relativistic jet, which is responsible for any observed short gamma ray bursts, is going to shock the ambient medium, which will give rise to a relatively long-lasting synchrotron afterglow. And as I'll show in the next slide, we can study this synchrotron afterglow to infer properties on the short gamma ray burst jet. In particular, we can get a constraint on the viewing angle of the jet, so the angle between us and the axis of the jet. And if we have that information, we can then infer this gives us for free the cos I term, the viewing angle of the gravitational wave source itself. And so the purpose of this talk is all about getting precise measurements on or constraints on the viewing angle of the relativistic jet to ultimately allow us to do a precise measurement of H0 using our bright siren. So there are two different kind of independent approaches one can take to analyze the synchrotron afterglow to infer different pieces of information. So in particular, the jet geometry, so the viewing angle of the jet as well as the opening angle of the jet, is going to impact the evolution of the light curve, as shown on the left. In particular, to first order, is going to be sensitive to the ratio between the viewing angle and the opening angle of the jet. And number two, shown on the right, is how the jet geometry is going to actually impact the location of the afterglow on the sky. So it's going to probe the difference between those two angles. Now on the left, we're looking at the light curve of 170817, which is by far our best kind of sampling of the sort of synchrotron afterglow to date. But even then, there was still some degeneracy in our interpretation of that event, of the synchrotron afterglow. And this really comes down, again, to the fact that the light curve is only really probing to first order the ratio between the viewing angle and opening angle of the jet. So then you can turn to route number two, shown on the right, to see if we can use spatial information at high spatial resolution to sort of break some of those degeneracies that exist if you just look at the light curve data alone. So on the right, we're looking at different examples of what the jet afterglow would look like at high spatial resolution for different combinations of jet viewing angle and opening angle. Now, to achieve these sort of resolutions that are required, so milliarc-second scales, we need to turn to a technique called very long baseline interferometry, or VLBI for short. This refers to the linkage of independent radio telescopes, in particular at large distances from one another, to increase your spatial resolution. So that's VLBI. That's what I mean when I use the word VLBI throughout this talk. So this is precisely the method that was used to observe 1708-17 to sort of break the degeneracies that we were getting when looking at the light curve information alone. So you can see the key plot from this nice 2018 Mouly et al. Nature paper. You can see there's clear evidence of proper motion, indicating that there had to have been a successful jet. They then compared these VLBI observations, these data, to those different afterglow model images that I showed in the previous slide. And they used that to find the best fitting model. And ultimately, they were able to place the constraints on the key jet parameters shown on the cartoon on the right. So here we're particularly going to be interested in the viewing angle of the jet. They were able to constrain it here to within between 14 and 28 degrees, which is unprecedentedly tight for a short gamma ray burst jet. So let's see how that impacted the analysis of the cosmology analysis. So you can see on the left this degeneracy that exists with the gravitational wave data that I mentioned between the distance and the viewing angle of the system by the orange contours. The blue contour shows what happens when you include this additional EM, VLBI, and light curve information. So essentially breaking that degeneracy. And on the right, we see the net effect that this has on measurements of H0. So you're really increasing the precision here. So clearly, these sort of joint VLBI GW data sets are incredibly powerful from a cosmology perspective. However, what I have not mentioned so far is just how challenging these VLBI data sets are. So to give you an idea for this, well, these are the radio images of 1708-17 in the VLBI data sets. Many of the challenges associated with these data sets stem from the fact that we're dealing with an intrinsically faint radio source. And this is going to limit our calibration options, and this is going to result in these residual astrometric systematic uncertainties that unfortunately are going to be comparable in magnitude to the very spatial changes that we are trying to probe. So for instance, the magnitude of the proper motion for 1708-17 that was measured was about 2.5 milliarc seconds. This happened to be moving along the left-right direction here. And you'll notice that this coincidentally is along the minor axis of our synthesized beam. So the axis along which we have the most resolving power. This was pure coincidence. So this, again, just underscores the importance of taking into account our astrometric systematic uncertainties that are associated with these VLBI GW datasets. And so the reality is for 1708-17, for the original analysis that was performed on the VLBI data, it was done in a sort of ad hoc way. And this is understandable because nobody could have anticipated such a data set. So we weren't really ready for it. But now 7 years has passed. And so for the last couple of years, I've been leading the development of this new kind of bespoke, purpose-built Bayesian model fitting framework that addresses all of these unique challenges that are unique to the specific science application. And for the remainder of my talk, I'll be presenting results that we have obtained by applying this Bayesian framework to do a reanalysis of the original 1708-17 VLBI data. So this is the first result that I'll show. So I'll walk you through this result plot. So the black data points correspond to the image plane location of the flux centroid of the afterglow of 1708-17. So this basically comes from those plots from those images that I showed in the last slide. So what we're doing is taking one of these model images as shown in the top left. We're going to fit them not to the images, but we're going to fit them directly to the correlated voltages that are detected by the radio telescopes. These are called visibilities. And we're going to take as our key free parameters the reference position of the models. We don't actually know where the merger occurred. We don't have that information, so we need to fit for that. we're also going to fit for the direction of the proper motion. And then we have a bunch of our systematic, our nuisance parameters for our systematic uncertainties associated with our VLBI data set. So the background blue and green data points are the resulting fits of that model to the data. And then the red data points are there to guide the eye. They correspond to the flux centroid of the fitted models. So essentially, we're looking for consistency between the black and the red data points. And you'll notice that we have consistency here. This model that we fit is actually what was found to be the best fitting model in the original analysis. So essentially what I'm showing with this plot is that we've kind of confirmed the results that were originally reported, only in a more statistically robust way. So that's great. But we want to see if we can go a step further. And it turns out that we can. So in particular, we can use Hubble Space Telescope observations of the kilonova to tell us about the position of the merger, whereas previously we're taking this as a free parameter. So more recently, Mouly et al. 2022 went through the painstaking steps of astrometrically calibrating this HST data set. And they were able to get this down to precision of a few tenths of a milliarc second. So that means we can actually now include this data point into our framework. So that means we're not going to be fitting anymore, taking as our free parameter the position of the merger. We are going to anchor it to this precisely measured position of the kilonova. And when we do that, we end up with the blue data points shown here. You'll notice that very clearly that what was found to be the best fitting model in the original 2018 analysis is no longer a good fit to this joint HST VLBI data set. So this means that, there's clearly some room for improvement in terms of measurements of these key jet parameters associated with 170817. So clearly, the issue is that the models that were originally considered explore the jet geometry parameter space too coarsely. We'd like to continuously explore this jet viewing angle, opening angle parameter space. And so to that end, we've developed this model scaling approach that essentially allows us to take a single 2D, a single jet simulation and its resulting 2D afterglow images. We can rescale them to any desired combination of jet viewing angle and opening angle using the sort of scaling relationship shown here. So essentially, we're going to be directly probing the difference between the viewing angle and the opening angle and the ratio of those values. So including that into our framework, you can see the resulting best fitting model images to the data. And you can see through this verification plot, it's kind of like a goodness of fit check. We have consistency between the blue and black data points, which is exactly what we want. But let's look at that posteriors. So you'll see that we have very good constraining power on the difference between the viewing angle and the opening angle, a couple of degrees, or within a couple of degrees. And however, we have no constraining power on the ratio between these values. And we really want a constraint on that value so that ultimately we can get a direct measurement of the viewing angle of the jet. But if you'll recall at the beginning of my talk, I mentioned that we can get this information by analyzing the light curve. It gives us the ratio between the viewing angle and the opening angle of the jet. So we can take an independent analysis. I've taken one here from the literature, which is a comprehensive analysis. And if we combine the constraints from the light curve analysis with the results from our Bayesian fit, we end up with this very nice constraint on the viewing angle of the jet of 170817, between 14 and 20 degrees. And you'll notice that we here have more than doubled the precision of this measurement from what was originally reported in 2018. So then the last step is to fold in the cosmology, right? So here this means we want to include 3 new parameters, in particular H0, group redshift, and the luminosity distance. So previously we were just holding the luminosity distance fixed, but now we're going to actually fit for this directly. And of course, we have 3 new likelihoods. We're including the gravitational wave information, peculiar velocities, group redshift, and we end up with the posteriors shown here. So in one global monster fit, we can obtain a constraint on the jet geometry. And crucially, we're finding that we can obtain H0 measurements for 170817 to a precision of about 10%. but doing this in a very statistically robust and rigorous way. So I'll leave you with my summary slide and happy to take some questions live. Thanks.
Thanks, Kelly. Any questions for Kelly, either in the room or on Zoom?
Hi, Kelly. This is Samaya here. Thank you very much for a very nice talk. I wanted to ask you about what your thoughts are on the horizon distance or the distance detectability of using VLBI measurements for future gravitational wave mergers. I remember it being about limited to about 80 megaparsecs to 100 megaparsecs, and what needs to be done in terms of upgrades, I guess, or future developments on the VLBI side in order to increase this, as well as actually just measuring the inclination angle from the light curve alone, and what kind of the state of the art and your thoughts are on doing this for sort of further away mergers which are beyond the VLBI detectability limit. Thank you.
Hi, Samaya. Really great to see you online anyway. Yeah, those are some really great questions. And we've been thinking a lot about that. So yeah, you were asking about the detectability. So indeed, we were very lucky, as many of us can appreciate in the room. I'm sure that we were lucky with the proximity of 1708, 17. This enabled us to be able to detect the counterpart with the VLBI networks in the Northern Hemisphere. And I already mentioned that one of the challenges is that this was already a faint detection, right? So that's a problem. And if we're talking about detections at 100 megaparsecs or 80 megaparsecs, we start to run into a little bit of trouble. We could basically compound the issues that I mentioned. There are a couple of future facilities or capabilities that I think might help to counteract this. So the SKA being one of them, absolutely. So I'd be really interested in seeing how we can apply this sort of science down the line by including the SKA. Providing VLBI capabilities on FAST is also going to help us boost sensitivity. One of my main concerns regarding your question, though, is our lack of a sensitive VLBI network in the Southern Hemisphere. So had 1708-17 occurred in, further south, and we wouldn't have been able to rely on, the high sensitivity array, which is what was used for the data that I presented here in this talk. If we only had to rely on the LBA in Australia, we wouldn't have been able to detect it, and that's concerning. So I'm really interested now in looking at ways that we can start strengthening the network in the South. And part of that's going to be looking at connecting the network to the SKA. So we have a few years to prepare for that. And I think I only answered the first half of your question, and now I forgot what the second half of your question is.
For the sake of time, perhaps we can take the second half of the question to Slack. Thank you again, Kelly. Let's get another round of applause for our speaker.
Thanks.
And we have one final talk in the session from Thomas Kupfer. So Thomas, please go ahead and share your slides.
Okay, perfect. Thanks a lot. So first, just to make a check, people can see my slides and I also can see the switch of the slides, right? Just make sure.
We don't see your slides yet.
Okay, I'm sharing actually. I do share. Try again. Try it again. Okay. Now I try it again.
Yes.
And when I play them, they change.
Yes.
Perfect. Awesome. Good. All right. Well, thanks everyone for being there. Sorry that I can't be there in person. But if you want to chat offline, please don't hesitate to either email me or write me a note on Slack. I'm pretty active there, at least reading. So please do that. Now, today I want to tell you a little bit about one really, I think, very exciting aspect for LISA, and that is that, or even though LISA is about 10 years away from launching, we actually know sources today LISA is expected to see, and those are the galactic binaries. And I want to talk a little bit about where we stand with the population there, and where we are going with that. And if you're interested in this list of sources, which we know are today are going to be detected with LISA, please look at this QR code. It's actually going to appear on every slide, so don't put your phones out and quickly get it. But if you want to see this list, please just look at it. So John has done a very great introduction, so I really won't go into details, but LISA is going to do this amazing instrument, seeing all these different kinds of cool sources which are interesting for their own interest, but really the bread and butter for LISA are going to be these galactic binaries, and these are these purple points here, which you see here, and then they're going to be more than 10,000 to be detected individually. If you think about it, every source below 10-minute orbital period in the entire galaxy will be seen by LISA, which is just amazing if you think about it. But on top of that, we expect to be about maybe 1,000, hundreds to 1,000 of those sources are being also bright enough in electromagnetic variance, so we can actually detect it in both electromagnetic and gravitational waves. And already today, even though we are far away from launch, today we can actually make this prediction and say which sources are going to be detected by LISA, and do a simple basically strain or gravitational wave strength and estimate, and just taking the trip masses, the orbital period, and the distance as you can see here. The trip masses and the orbital period, something we measure from photometry, spectroscopy, all these different tools. Now the distance was always a bit of a bottleneck historically, because we didn't really have good distances for many sources. Now this changed in 2018 when Gaia was launched. Sorry. This changed in 2018 when Gaia was launched, where we had for the first time parallaxes for millions of sources, and we could actually provide these estimates for the gravitational wave strengths. And in 2018, when this came out, we did this. We took all the sources we knew at that time and estimated their gravitational wave strengths, and that's what you see here. Now you see the different colors. Those are different types of sources. You see in blue, let's start basically go through them one by one. So in blue, the blue diamonds are what we call AMCVN systems. I'm pretty sure not everybody knows what an AMCVN system is, but basically those are stable accreting white dwarfs with periods below an hour. So the white dwarf is accreting, and because it has a very tight system, it has to be a white dwarf or helium star, donor star, typically very helium-rich object. So kind of the cataclysmic variables, but instead of a main sequence donor, you have a white dwarf or a helium star donor. The red circles are the historically known double white dwarfs, or detached double white dwarfs just orbiting. Then we have this yellow triangle, which is actually an SDB, or compact helium star, which lost its hydrogen envelope, orbiting with a white dwarf. And then in purple, we have this ultra-compact X-ray binary. That's an accreting neutron star with a white dwarf donor star. Now in 2018, you see that most of them are blue. Those are the AMCVNs, and that's just because they are much easier to detect. They are really easy in spectroscopy to find because they are dominated by the accretion disk. But in reality, that's probably not what we expect. So then we started was that, okay, let's do this much more systematically. Let's find more system in a much more systematic way. And there were several surveys starting, and I was part of one of them, which was the Zwicky Transient Facility, which is a photometric survey which observes the sky repeatedly and then basically looks for changes. And we had a dedicated survey of galactic plane fields, which you can see here in the orange and red boxes. Those are individual fields. And we basically, what we did was we went to each of these fields, and we continuously observed this field for a few hours straight. And what you get from that is an example in the lower left, where you see a light curve, photometric light curve, over an hour and a half. And you see this particular object is a 40-minute binary system. And you see basically the repeating pattern, in this case, of an eclipse. Right? And what you basically do is you do this for many fields. And then you basically pick out all the light curves, and you search for very short periodic variability. Now, that's really a needle in a haystack search. If you think about it, we covered a few 100 million objects, stars, and we found several new LISA sources, right? So this was great, but it's still not straight. Was not easy. And before I show you now, so this has been done basically for the last couple of years, and there has been other surveys also doing that. And basically, before I show you now where we stand as of today, we did something else too. So historically, we said, well, LISA is going to detect a source if the gravitational wave amplitude is SNR 5 or higher above the noise for LISA. Then we call it, historically, we called it a verification system. Well, maybe that's not the best way to do it. well, maybe it's better to, instead of doing that, we actually simulate the LISA data. So simulate LISA data for a particular source where we know the masses, period, and everything. And then we put it in the kind of foreground noise LISA box, and we say, okay, can we pick it out of that box? Yes or no? And if the answer is no, then it's not detected. If the answer is yes, it's a detectable system. And I'm showing we used for that particular case, there's more tools out there, but we used a very strong collaboration with Tyson Littenberg, the LDA soft code, which also includes EM priors like sky localization, frequency, distance, and so on. And then we did this. So here's an example, SCSS J08 2022, which we call non-detectable, because what you see here is every time, every realization after 1 month observing with LISA, 3 months observing, 6 months, those are the different colors. We basically only recover the Gaussian prior of the inclination as an example here, right? We basically see this broad profile for the inclination, and that's basically just the input prior we put in for inclination because we didn't really know, so we just put in a random, basically a Gaussian prior. And because it's basically only recovering the prior, we say LISA has not detected that source. So that's what we call non-detectable even after 4 years. If a source over some time, and you see this here as an example with CTFJ 2029, you see that after some time, this broad Gaussian prior for the inclination is actually really narrowing down to a very narrow Gaussian profile. That is actually at this point, we say, now it's a detection. Now we actually can recover that source with LISA. And in this particular case, this happened after more than 6 months. So we actually said it's a detectable system. And if a source, we see this down in the lower left, that's a very exciting system, CTFJ 1539, it's a 7-minute system. Already after less than 3 months, we actually see this prior basically going away, and we very narrowing down. Basically, we detect the sources in less than 3 months. We call it a verification system. And that's really the difference. Historically, a verification system was everything, but it's really, if you detect a source only after 4 years, it's not really verifying anything anymore. So we said, okay, let's say if it's less than 3 months, we call it a verification system. If you detect it within 4 years, but in more than 3 months, it's a detectable system. And even after 4 years, it's not detected. It's basically undetectable. Okay, so that's where we stand now. So what are we, where we are now? Well, first of all, the good news is we really added many more systems, and not just we, many different types of surveys did. We basically tripled the numbers from 17 to now 40 systems. Out of those 40 systems, we expect 18 to be detected after less than 3 months, which is really great across the sky. But now still, so this is really great, but now still the caveat for this. First of all, well, we added many more red systems. You see this in the upper left strain plot, many more red systems, which means many more double white dwarfs. But you see many filled symbols, and those filled symbols represent eclipsing sources. So those are sources which are eclipsing, and half of the known sources are eclipsing. And the reason basically is they are easy to spot in photometric surveys. So that's the one thing. So still this bias towards eclipsing systems. The other thing, if you look in the upper right, you see in Hatchman-Russell diagram, you see the main sequence in the dark area, and then you see the white dwarf track much lower, and then you see most of these sources are well above the white dwarf track. That's kind of a bit of an issue because that's not where we typically expect them, but they're much brighter. These are younger white dwarfs, hotter white dwarfs systems, so we can actually spot them much easier. And that's why we are still there. So we would expect most of them actually fall on the white dwarf track. And the other thing, if you look in the lower right, you see the sky distribution of the sources. Upper part is northern hemisphere, lower part is southern hemisphere. And because most of the surveys were done in the northern hemisphere, like CTF, for example, most of the sources are located in the northern hemisphere. Right? So it's still this bias to the north. Now, this is for sure going to change over the next few years because BlackGem is online running and observing similar survey in the galactic plane as we did with CTF, and then also where Rubin is coming online and also will add here. So we probably will certainly fill this gap in the lower side. So the point is, we did a great job over the last years to build a much more systematic sample of objects, but we are still only scratching the surface because we still have these biases, and that's something we'll work on heavily over the next 10 years. And I'm almost betting that by the time these are launches, will be 100 systems and have a much more systematic, better understanding of what the sources are. So this is actually pretty exciting. because this is when we wrote this paper, we almost had to go to a second page, which for the number of sources is pretty cool. So this is the number of sources. Now, the only caveat I want to mention here is that for many sources, we actually have very good estimates, but not for all of them. And in particular, these AMCVN systems, which are these accreting white dwarfs, are kind of a blessing and a curse. A blessing in the sense of accreting white dwarfs have these accretion disks, so they're easy to find in surveys. But accretion disks also a curse because it makes it much harder to measure actually masses and all the details about it. So up to now, many of those systems, as you see here in blue contours, the M1 and M2, these are the masses, are in brackets, and that means we have the assumptions. We don't have good measurements of those masses. And that's something we still limit a little bit. And I think Lisa is going to do a really, really good job helping us to limit that. And for the sake of time, I will actually not talk about that anymore. But if you want to chat offline, we actually currently run simulations to see where actually Lisa can add information which we do not get from electromagnetic bands just by the limit of what we can do from electromagnetic side. But if you want to know more, please contact me online. And so I will go straight to my summary and basically say that in the early times, it was really only serendipitously done, these discoveries. We have done a much better job over the last few years, and we're actually continuing this. The sample is still biased towards luminous and northern sources, but we actually get better there. But we are expecting many, many more systems, and it will be, by the time Lisa flies and turns on, we'll probably have tens of maybe 100 sources, which we can do multi-messenger studies, which is, I think, great, and we can combine this. And so with that, thank you very much for your attention, and I'm happy to take any questions.
Time for a couple of questions.
Hi, Thomas, Darwin. It's a great pleasure to see you virtually. So you have done an excellent job. So most of your closed double white dwarfs, that's eclipsing ones. So if they are not eclipsing, so what would you expect? What I mean, the production of non-eclipsing double white dwarf, what that would be?
Yeah, so the non-eclipsing double white dwarfs are, if they're really, really close, we see ellipsoidal deformation. So the white dwarf is tidally deformed. And as it goes around, you see in the photometry in the light curve, the round shape or the X shape, which is kind of leading to a photometric variability. That's one thing, but then they have to be already really close. Now, the other thing is, and that's something we are doing right now with SDSS5 and LaMoste and all these spectroscopic survey. Of course, those white dwarfs, they show really large radial velocity shifts. Even if they have a period of an hour, they show hundreds of kilometers radial velocity shift. So the only thing you have to do is observe every single white dwarf with multi-epoch spectroscopy and then look for the ones which show the largest radial velocity shifts, and then take more spectra to find the orbital period. And that's something which we're working on right now really actively in SDSS5 and also in LaMoste to do that and find these systems that way, which do not show any photometric variability. Yeah, but that's harder. It's much harder. That's true.
Hi, Thomas. My question is regarding the detectability software that you talked about. The question is that would you tell us a little bit more about what goes into the main principles of this software, particularly how do you take into account a lot of overlapping signals, what we call the foreground noise, for example.
So if you really want to know all the details, I really refer you to Tyson Littenbeck because he wrote the code and he knows the details. But yeah, so what it's basically doing, it assumes a foreground which comes from binary population studies. So those are, right, this is the best way currently we estimate the foreground. So assuming this curve, this noise curve is basically the foreground is coming from binary population studies. That's included there. And then it's really, you run the simulations, basically you estimate your gravitational wave signal, and then you say, can you pick it out? And you include things like sky localization because it makes it easier to pick it up. If you include the sky localization, it's much easier to pick it up. If you know the frequency already, then it's also easier to pick it out because you basically know which frequency bin you have to look at. So it goes all into now how this on the technical side really works. I would refer you to Tyson. He really knows that.
And what is the signal to noise ratio you typically take?
Yeah. So to call it detectable, we typically get around 5-ish. So it depends a little bit on the sky exactly, because then the sky is not uniform, right? There's more foreground in the bulge region, for example, because there are much more sources. So there you need a little bit of a higher SNR, signal to noise, but it's around 4 to 6-ish. Yeah.
Okay, thank you very much.
Yeah.
Okay, great. Let's thank Thomas and all the speakers and the AV staff for this session again.
intense on and you speak. All right, it's time to get the afternoon session started. So good afternoon, everybody. I'm Stefan Ballmer. I'm going to be chairing the first part of this. First, we have one announcement, just a single slide, and then who is the first speaker in the afternoon? Alessandra? You're going to be also the speaker afterwards? Okay, yeah.
No, the second speaker, I think he was there.
Okay, all right, sounds good. Okay, the floor is yours.
May I also have this thing to change the slide?
I think it's up there, right on the podium.
Right.
And make sure your mic works.
Hello, can you hear me? Okay, great. So good afternoon, everyone. My name is Aleksandra Olejak, and I'm currently postdoc fellow in Max Planck Institute for Astrophysics. So this is Lisa's session, but I will actually talk about more about LIGO Virga sources. So I will talk about formation channels for binary black hole mergers that were already addressed during the few talks last days. So as we all know, there are around 100 gravitational wave detections publicly announced, and they are vastly dominated by binary black hole mergers. And there is around 100 more that are still not published, and we are really looking forward for them to be publicly announced. And as the population grows, of course, there have been many works already trying to find some general properties of this population, like the mass distribution or the spin distribution that could somehow indicate contributions of different formation channels. However, due to many uncertainties in modeling of those formation channels, the actual origin of detected population of gravitational wave sources is still highly uncertain, and we still don't know which channels contribute. So recent literature suggests several formation channels that could contribute to formation of the detected population of gravitational wave sources. And I think the most popular is this isolated binary evolution channel with common envelope, and this recently more popular stable mass transfer channel. And the second very popular channel is formation in the dense stellar environments, such as globular clusters. However, there are also other possibilities, such as some formation in the triples or higher multiple systems, formation in the AGN disk, or even more exotic formation scenarios, such as primordial black holes. So today, I will focus on those two variants of isolated binary evolution. So for many years, when you were talking about isolated binary evolution formation scenario for binary black hole mergers, it was almost equivalent to this classical formation channel with common envelope during the second Roche-Lopp overflow in the system. So as you already heard during last talks, common envelope seems to be like a very promising mechanism in order to shrink the orbit of initially wide binary system to form a close binary black hole system that is able to merge in the Hubble time. However, several recent studies challenged significant contribution of this formation channel, and this is for several reasons. First of all, as you already heard, for example, in the talk of Anna Chiara Pico or Pablo Marchand or Hongwei Ge, the mass transfer in such a massive binary systems like binary black hole progenitors is probably much more stable than was previously thought. And the second thing is that even if you develop unstable mass transfer in the binary system, it is very hard to get successful envelope ejection and avoid the stellar mergers. And it seems that it's only possible under very restricted conditions for the donor star. Therefore, it seems that those rapid population synthesis code strongly overestimate number of successful common envelope ejection and contribution of this formation channel. And during the recent years, this new formation channel with 2 stable mass transfer episodes is gaining a lot of attention in the community. And in our models, once we implemented revised mass transfer stability criteria, this stable mass transfer channel actually dominates the rates for the formation of binary black hole mergers. So in our models, the stable mass transfer channel consists of relatively conservative mass transfer during the first Rorschach overflow that often leads to mass ratio reversal. And then we have the second stable mass transfer episode, which is highly non-conservative with the black hole accretor. And it is often assumed that the angular momentum loss of the mass that is not accreted by the black hole is lost with the specific angular momentum of the accretor, which is rather the lower limit. So those assumptions, highly uncertain assumptions, such as how conservative is mass transfer and what is the angular momentum of the mass that is ejected from the system, impacts a lot the properties of binary black hole progenitors in our simulations. So once following, as you can see, once following response of the orbital separation to the stable mass transfer, you can see that you can only shrink the orbital separation of the system once the donor is more massive than the accretor. And this is especially evident for the conservative mass transfer. And once you have highly non-conservative mass transfer, which is believed to be the case once the black hole is the accretor, then a lot of depends also on what you assume on this highly uncertain parameter, which is gamma, and which corresponds to the angular momentum of the mass that is ejected from the system. So in our default model, where, as I said, we assume that this angular momentum is rather low, we have this characteristic parameter space that favors binary black hole progenitors for the stable mass transfer channel and common envelope channel. So as you can see, for the stable mass transfer formation scenario in our default model, strongly favors unequal mass star black hole binaries on moderate separations, while a common envelope favors wider binaries because in order to fit a giant with already well-developed convective envelope and avoid the stellar merger. So yeah, as I said, this assumption on the angular momentum loss from the system is highly uncertain. And actually, several recent works indicates that this loss of this value of the specific angular momentum could be much higher than is popularly assumed in those rapid population synthesis code. And for example, some part of the ejected matter could be lost even through the outer Lagrangian point. And once we allow for much higher angular momentum loss in our simulations during the second Rorschach overflow, as you can see, the parameter space for binary black hole progenitors changes drastically, and the binary black hole progenitors in our previous models with the low angular momentum loss merge during the second mass transfer phase, while the more equal progenitors are able to shrink the orbit and form close binary black hole mergers. So, of course, those different assumptions and this thing that our our binary black hole progenitors favors some parameter space, later affects the distribution of the produced binary black hole mergers. And as you can see, for example, in our default model, due to this preference of highly unequal mass binaries that can only shrink the orbit with a low angular momentum loss, you get this characteristic peak for mass ratio, which is around 0.6 for the stable mass transfer channel. While for a common envelope channel, at least in our very simplified approach with this alpha prescription, binary black hole progenitors favors rather equal mass binaries. And everything changes once we allow for more angular momentum loss during the second mass transfer phase. Then also this peak disappears and stable mass transfer also favors formation of equal mass binary black hole mergers. There are also other parameters which are are important in the context of binary black hole formation, such as the natal kicks that black holes get during their formation. That could also affect the shape of distribution of mass ratio of binary black hole mergers. This could be interesting because recently there have been several few alternative analysis of gravitational wave detections, which in contrast to what was previously said, they claim that they find some evidence for contribution of unequal mass binary black hole mergers in the population. And some of them, this one is actually quite extreme, but as you can see, they find some evidence for this peak around 0.6 when it comes to mass ratio of binary black hole mergers, which is very consistent with what our default model. So of course, these assumptions on mass transfer stability and the loss of angular momentum also impacts, for example, distribution of time delays. So the times between the binary black hole formation and its merger due to gravitational waves. And then it also affects also, for example, evolution of the merger rates as a function of redshift. But let me tell you now something quickly about our work on black hole spins. So current population detected by LIGO Virgo seems to be consistent with the population dominated by low spinning black holes, low spinning but non-zero spinning, with some tail extending towards high black hole spin values. So such observation that black holes tend to have low spins points towards efficient angular momentum transport in the massive stars, because you need to have some sort of mechanism that is able to transfer mass from the rapidly rotating core towards the upper layers of the star that are later removed with the stellar winds or mass transfer. Observation indicates for efficient angular momentum transfer in the massive stars. However, in order to reconstruct the full distribution of the black hole spins, we need to have also some mechanism that is able to produce some fraction of highly spinning black holes. And therefore, in our simulations, we also allow for the tidal spin up, which was theoretically predicted. That when you have a close black hole helium core binaries on the orbital separation below 1 day, the secondary form black hole could be tidally spin up by the black hole and produce highly spinning secondary black hole. So once we allow for those both assumptions. So we assume that angular momentum transport in the massive star is efficient. And once we allow for this tidal spin up in the close black hole Wolf-Rayet binaries, we are able to quite well reconstruct distribution of binary black hole mergers, the spins reported by LIGO Virgo. And moreover, we find that combination of stable mass transfer channel and common envelope channel in our models is also produce some interesting patterns in when you look at the distribution of effective spins and mass ratio, which could be consistent with the correlation that has been reported by LIGO Virgo. So to sum up, yeah, the origin of detected binary black hole mergers is still unknown, and there are several formation channels that could contribute. Isolated binary evolution channel is quite well reconstruct all the properties of detected population, even the more exotic events or the correlation between the spins and the mass ratio of binary black hole mergers. The stable mass transfer channel is relatively new formation scenario and requires more studies, but it is promising formation channel that could contribute to formation of current population. And maybe properties such as mass ratio of binary black hole mergers, which unfortunately is not derived in a very robust way currently, could tell us something about mass transfer in massive binary system, which are progenitors of binary black hole mergers. Okay. Thank you for your attention. And
thank you, Alessandra. You have time for one question. Yep, I see one hand there. Yep, the microphone's coming down.
Hi, Alexander. I have a question regarding the L2 mass leak that you talk about. The
Yes.
question is that could you give us like a hint of how much mass is lost from the L2 point? Because I mean, in particular, whether it would form effectively a sufficient circumbinary disk so that after the merger it is also an intelligent source for electromagnetic counterpart.
Yeah, you're right. I mean, yeah, currently it's very uncertain, and people are trying to find like some fraction that could be lost through the outer Lagrangian point using some hydro simulations. But in fact, this like the formation or the circumbinary disk could also affect like the like what is the like going on with the angular momentum of the system and how much angular momentum is conserved. And I don't know, probably people think about some observations, but as you know, it's hard because massive stars are rare, and those mass transfer phases are even much more rare and very short. So
yeah, it's interesting. That's what I thought about. It was also a good source for electromagnetic counterpart after the merger.
Yeah.
All right, let's thank Alessandra again. And we're going to move on to the next talk, which is Sayan Basu.
Yeah.
Yep. The clicker should be up there. Yeah, it's coming. Who's talking about the radio view of PG 1302-102. Floor's yours.
Good afternoon, everyone. Oh. 1, 2, okay. Good afternoon, everyone. Okay, yeah. I'm Sayan Basu. I'm a postdoctoral researcher at University of Witwatersrand, working with Professor Roger Dean. So today I'm going to talk about the radio view of PG 1302-102, a potential black hole binary candidate for gravitational wave emission. So this is the outline of my talk. So I'll start with a short introduction about supermassive black hole binaries. So binaries form in course of the galaxy mergers, and they are key components in our understanding of galaxy evolutions. So after merging of the galaxies due to dynamical friction, so the supermassive black holes, they form a bound pair at a separation of parsecs. And as the binary hardens, their orbit shrink down, orbit will shrink down due to the gravitational wave radiations, then leading to a final coalescence and accompanied with a very strong burst of the gravitational wave emission, and followed by a recoil of newly formed single black hole. And in the below panel, it shows the evolution duration of a black hole binary depending on their orbital separation. However, we know that the gravitational wave emission will play an important role for the black holes to merge. But what happens and what are the processes that brings them up before that stage? And that remains a problem, and this is known as the final parsec problem. So last year there was a paper by Nanograph collaboration who reported the evidence of gravitational wave background using 15-year data from pulsar timing array. And this is an artist conception of concept of gravitational waves. So this is closely orbiting two supermassive black holes, and they emit gravitational waves, which represented here by the ripple in the space-time. And here I show the evolutionary stages of supermassive black hole binary candidates with some of the candidates and their orbital separations as well. So now I introduce the source that I'm currently working on. It's PG1302-102. It's a bright flat spectrum radio quasar at a redshift of 0.278, hosted by an elliptical galaxy. So the source became very popular when Graham et al. In 2015, they reported an orbital periodicity of 5.2 years using CRTS V-band optical data. So this is the V-band optical light curve. From 20 years of observations that reported by Graham et al. And the red line here is the sinusoidal fit with a period of 5.2 years time. And this periodicity, they just interpreted this periodicity to be a consequences of an orbital motion of the black hole binary in the system. And the study also suggested that the projected separation between two black holes in the system to be 0.01 parsec. However, they also did optical and UV light curve. So the red ones are near UV and the blue ones are the far UV. And even from here, we can see the sinusoidal fit is like about 5.2 years time. So based on the optical and UV, they interpreted that PG1302-102 is a black hole binary candidate. And then later, when Liu et al. 2018 added more optical data to the light curve by Graham et al. 2015, they found the signature of the periodicity decreased. So here, the blue ones are the data that they have added from its SSN optical survey at V-band, and here they produced a synthetic light curve under damped random walk model, and this is the periodogram. And from this analysis, they came into conclusion that the periodicity from 1884 days, so they calculated to be 2012 days. So they argued that it might not be a black hole binary candidate based on the light curve analysis that they had. So we thought maybe we can do something in the radio. So we looked at the ATCA data, ATCA multi-frequency observations, and then we plotted the radio light curve of PG13 using all the available observations here. And we highlighted the 5.55 gigahertz because it has the most number of observations. However, this is the radio light curve of PG13 from 2005 until 2023. So it's like 18 years of light curve. Then we fitted the sinusoidal fit with 5.2 years time as reported by Graham et al. And then we found that it's like aperiodic. So we thought, okay, so let's just have a look at the spectral index. But what happened is like we didn't have enough observations in 5.5, 5.5, 2.1, and 17. So we decided, okay, so we'll look at the in-band spectral index time series. So this is the in-band spectral index time series where we fitted the sinusoidal fit again with the 5.2 years time reported by the Graham metal. The in-band spectral index, they are actually very useful to understand the interactions between the accretion disk and the relativistic jet in the supermassive black hole binaries, and also monitoring spectral index over a period of time. We can even get some ideas about the orbital decay and the merging process as well. Okay, so then what we did again, like we divided the entire in-band spectral index time series into 2 portions. It's like pre-G15 and then post-G15. So the pre-G15 contains the data from 2005 until 2014, and then the post-G15 contains the data from 2016 up until 2023. So what we did, we calculated the periodicity using the Lomskargel pierogram method. So for the time constraint, I just show the PG15 analysis that we had. So this is the LSP of the PG15 light curve, and then we got the number 5.2 years also. And for post G15 periodicity, our calculated periodicity was 2001 days. However, to calculate the uncertainty on our periodicity, what we did, we ran Monte Carlo simulations, like 10,000 random permutations on spectral index while keeping the time constant. And then the uncertainty we measured was half width, half max of the spectral peak. And in this table, I show you all the numbers that we had. So these are from the radio, and these are from the optical. So then we came in the conclusion that somehow radio and optical, they are coupled together, even though they are from the two different mechanisms. So then we thought, okay, so under which kind of possible scenario in a black hole binary model it can happen? So the Graham et al. Paper, they already mentioned like the optical and UV periodicity comes from the accretion disk. And we thought the radio periodicity may be from the precession of jet. So what happens is like the whole jet precesses, and all the superluminal knots that ejected in the different times, they follow the jet axis. And thus they form a helical jet pattern, which Kuhn et al. 2015 using VLA 1.4 gigahertz map, they actually showed, okay, so what they showed is that northern part of the jet actually shows a helical jet. However, the southern part doesn't reveal a helical pattern. However, it's a different kind of shape that it has. And what Kuhn et al. Suggested that it might be the jet cloud interaction in the southern part. And so now what we have is like we have periodicity in the optical V band, 5.2 years time, and then Quinn et al. 2018 using the Mojave 15 gigahertz VLBI map, they calculated the precession period of the jet to be 5.2 years time. And then what we did, we used ATCA 5.5 in-band spectral index, periodicity also got us 5.2 years time. So that's how we came to the conclusion that radio and optical, they are coupled. So we thought that PG 1302 minus 102 is in fact a supermassive, it might host supermassive binary black holes in which one black hole emits the radio jet and the other one the other one okay, so the periodicity in the jet precession that we have, it comes from the primary black hole that emits the radio jet, and the optical one comes from the accretion disk. So it actually matches the orbital motion. So it matches the model that Graham et al. Proposed with the orbital motion of the two black holes. So the orbital motion of the jet emitting black hole, it actually produces the jet swing, and then the optical variability comes from the accretion disk of the secondary black hole. So if confirmed, then PG 1302 minus 102 will fall in this regime of the gravitational wave, and it will be a big thing in the near future if it's confirmed. So in conclusion, we couldn't find any signature in radio light curve. However, the pre-G15 light curve, in-band spectral index light curve shows the periodicity to be similar to the optical periodicity that Graham et al. Reported. And the post-G15 periodicity, they are also similar to what Liu et al. 2018 reported in the follow-up optical observing paper. And then we concluded that the radio and optical, they are coupled, despite being two different emission mechanisms. However, to confirm the periodicity in both and optical, we need more follow-up observations both in radio and optical. However, despite the change in the periodicity, PG1302-102 still remains a strong binary supermassive black hole candidate. Yeah. Okay, so future work. So we thought maybe we can also do some VLBA imaging of the source. So these are the preliminary imaging of the source at K-band. So we decided to put a proposal next year where we'll just do the imaging of PG1302 at higher frequency. So maybe in the higher frequency, the putative black hole will be resolvable. And then ongoing and future wild field synoptic surveys will have more binary candidates like PG1302. And another thing is like it can be an interesting candidate for the next generation EHT observations. And future South African EHT site will dramatically increase the image fidelity. So please see Senkosi's poster on Monday. And then we are gonna very soon we are gonna start imaging of a post-merger survey, and in which we expect to reveal more binary candidate maybe. And yeah, so I finished my talk saying this guy, he happens to work for the Gravitational Wave Research Group in Australia, OZE-GRAB. And recently he won a gold medal in 50-meter Olympic swimming. So he carried a gravitational wave sighting in his swimming cap. Thanks.
Thank you. Unexpected publicity. Any questions? Actually, while we ask question, is the next speaker Metinata around already or online? Yes. I see. It's too bright. I can't quite see. I assume that's a yes. No. Okay. All right. So we might have to speak that. So that means we have definitely time for questions. Any questions for Sayan?
Hi, very nice talk. I was wondering, maybe I missed it in talk, whether you have any idea what cost the widening then? Or like
Sorry?
What cost the change in period, do you think? Do you have any idea?
So what happens is like it's not like OJ287 where the black hole goes through the accretion disk in every 12 years. So it's like two black holes and then they goes around like this. So when it's like here, then we have like this periodicity we see in the optical light curve.
No, but like what cost the change with pre-15 and post-15? Do you have any idea?
Oh, okay. So with that one, I would like to say like for PG1302, we really don't have this sinusoidal pattern of the light curve every single time because Carisi et al. They use optical B-band light curve, and there was no sinusoidal pattern in the light curve for 20 years time from 1935 up until 1955. So it can be that at that time, like the optical flaring in jet was just overshadowed the light curve or maybe something like that. And these things, it seems like it can also happen like the due to the low accretion rate. It can be another cause, but these things are like temporary flaring kind of thing like we see in the light curves.
Okay, there's another question.
We also have an online question. Thank you.
Yep. Okay. why don't you go ahead if you have a mic, and then we go to online.
Hi, thank you for the talk. If I remember correctly, you said that the separation between the supermassive black holes is less than 1 parsec.
Yes, 0.01 parsec. Yes.
So can these observations be used to give some empirical constraints on the final parsec problem?
Yeah, it can, but for that one, like they did the calculation for the separation between using the spectroscopic observations. But first of all, we need to confirm that it's a binary. And then we can just put constraint on those kind of conclusions.
Thank you.
Okay, we had an online question.
Thanks very much for the nice talk. I was wondering whether the periodicity which you were showing could also be explained by disk jet interaction in the quasar, where the interaction between the two can couple the radio emission with the optical variability. And if so, since the orbital period is supposedly 5 years, would a high cadence campaign of the type like the in-band spectral index and optical observation, would that be helpful in resolving the question of the periodicity?
I think so. But first of all, like we need more observations first to see like whether it is a binary or not. But yes, thanks for the comments. Yeah, it will be helpful in the future.
Okay, let me ask you, is the next speaker, Gerardo Sanchez, already ready? Yeah, start, prepare yourself, and then if there's any other question, we have time. I don't see any hands. Okay. Let's thank Sayan again. Okay, the next talk will be from Gerardo Sanchez on gravitational wave memory from the propagation of long gamma ray bursts and their detection by future space-based interferometers. And he's still setting up the mic, so we have a minute or two. And since we have a minute after that, will be Surajit Kalita. Is he here? Yeah, you can start getting the mic set up during the current talk. No problem at all. Not your fault. The floor is yours.
Yeah, thank you. Good afternoon. I am Gerardo. I am a postdoc in Warsaw at the group of Professor Janiuk. I will be speaking about numerical simulations of long-range GRBs and how it looks like the gravitational wave emission extracted from these simulations. Yes, so far we have been hearing interesting discussions about the different sources at different frequencies from ground-based telescopes and the future detection by space-based telescopes. No, it will be exciting to know new gravitational wave sources in low frequencies, and our concern here is what happened with gamma ray burst. And yes, as plenty of you know, gamma ray bursts are very exciting explosions, mainly arising from binary neutron star mergers or binary black hole neutron stars, or during the collapse of massive stars. So it could be distinguished with the duration. And yes, some years ago, as you know, we had the first example of multi-messenger observations of this kind of guys. It was exciting to know a better constraint and improving of our understanding about this kind of explosions. Thanks to the gravitational wave emissions, we know important properties from the central engine as the mass of the neutron stars and what happened with the delay was an important thing in this event, the delay between the gravitational wave emission and the electromagnetic counterpart of the gamma rays in the jet. We observe a lot, this exciting transient, the kilonova powered by the our process mainly and the late afterglow emission. But however, there is some dark knowledge about GRBs. For example, in the next slide, I will be speaking about of long gamma ray bursts. It is an example of simulation of magnetorotational core collapse that we are working now. Basically, here we have a magnetized core, and the material is falling around in a curved black hole. The Blandford-Snarek mechanism is activated by the amplification of magnetic fields, and the jet is collimated, and it allows to drilling the star, and finally propagate until the boundary and get a successful breakout. And after that, the history is not the end here. The jet continues to expanding to the external medium. The dark knowledge of GRBs is in the first milliseconds. The jet acquires its main properties during the first seconds of propagation inside of the progenitor star. But we have, notwithstanding, we have a better, we understand well how the electromagnetic counterparts are produced at very large scales. But at the beginning, it's impossible because the source is highly relativistic, it's beamed, and we have here high opacity, and it doesn't allow us to see some electromagnetic counterparts. But here our purpose for this work is, can gravitational wave signals provide us information in the first milliseconds of the jet propagation? It is the purpose. We have been, for that, we have been using this analytical model, the so-called gravitational wave memory. Basically, it's based the linearized version of the field equations, taking into account in the energy stress tensor a blob massive mass traveling along our line with very fast and very energy. The solution is a well-known potential, the generalized form of Leonard-Bicher potential. But here the important is by obtaining the transless components. I mean the extraction of the main geometrical components. We can see here in more human quantities for better understanding. I mean, here the model, the important thinking, the important quantities of the model is the energy of each blob of matter, the velocity, and the geometry, because it is strongly independent of how the projection of the velocity in the fluid frame is changing. It will be important because the fluid has some turbulence, is traveling by a chaotic way at the beginning, and it depends of the observing angle. It is this model is very nice because it could be applied to numerical simulation. It is my computational box, for example, and each fluid of parcel at the end of the estimations, we take into account the contribution of every fluid of parcel. So yeah, let me speaking about fast of the initial condition for the simulations. For this project, we are running special relativistic hydrodynamical simulations in adaptive mesh refinement code. The name is mezcal. This alcoholic Mexican drinking. But yes, Italian. It's made by the Italians like call coats as alcoholic drinks. No, but I'm sorry. Yes, we implement this jet as a strong jump conditions in a pre-collapsar stripped envelope. We took this model by Husli Heger. We implement very far for this project, very far from the black hole. The jet, we assume that the jet is already successfully crossed the more massive region of the star. We implement here the initial conditions and we follow. It is something like a virtual laboratory, the numerical simulations. It is an example of which models we are running. In particular, we are running successful jets. We control the parameters, no? How much energy we are injected in the jet, how much time, how much luminosity, and implementing various recipes. For example, this is a successful jet. It's a very collimated jet, and it propagates during 300 of seconds. I mean, we can follow since the very dense part of the star until the external environment. Here, the jet is crossing a supernova injected as a thermal bomb. And here is the failed jet. We are also interested in that because now are in discussion this kind of models for looking what kind of transients can be produced and typical supernova. Yes, the next question, using this analytical model via post-processing, we run simulations, and after that we take the all hydrodynamical data, we did the post-processing, and here is an example and for which region the gravitational wave emission is produced. Basically, as you can imagine, this is a map of asymptotic velocity, which is basically estimated by the Lorentz factor multiplied by the enthalpy. But we can know how much energy with this kind of maps, the most energy material and more faster are denoted by red. Here I put a different stage of the evolution of the jet. It is funny, this kind of map, because while, yes, in this kind of models, we can observe how the jet shock front travel more lower with respect the material coming from the central engine. At the end, the faster material and high energetic material becomes in a shell. That in the future becomes a self-similar blast wave. No? Yes, coming from the first question that I tell you is what kind of observations could be observed with this gravitational wave memory. I was wondering about the main properties of the jet, and it could be show this kind of observations can provide us, for example, how much energy is extracted from the black hole. It is important because many models for emission of GRBs need this time, the injection time for estimation, no? For electromagnetic multiparts. Another important is when the breakout is get. Here provide us information on how much large is the progenitor. And finally, the acceleration phase, which is the final coasting phase of the jet. And here I show an example of how this signal could be changed by different observing angles. Finally, the most important thing is the detectability. Yes. Here we took the Fourier transform for estimate the amplitude spectral density, which is the Fourier transform multiplied by the square root of the frequency, for the comparison with the future space-based telescope. Now, here unfortunately, for example, this model is estimated from a jet with energy 10 to 52 ergs, very energetic, and a distance of 1 megaparsec, no, nearby. Yes, it's an overestimation. Sadly, this model, for example, it's below to the curve of Lisa. No? but a future space-based telescope like the Big Bang Observer could be possible to detect. These curves means the different observing angles for this jet. The observing is the angle of observation is measured respect the jet axis. Also, here only I want to present some estimations of rates of detection per year with future space-based telescope could be possible to observe 8 GRVs per year, for example, depending on the observation angle. And but what happens with high frequency? So now it's in discussion this if the possibility of looking for, there is some persons claiming for high energy observations in high frequencies, but for that we need more resolution. That we also we are working on that, changing the methodology by implement this analytical model together with the simulation. It is important because the time steps in the simulation, the resolution is very high. It's about 10 to minus 4 seconds, 10 hundredths of milliseconds. And we can observe, for example, here I put an estimation of this strain, the evolution of the strain, with different time evolutions, just for looking for high frequencies. This is an example of how this signal looks like at high frequencies, very wide range of frequencies. Here I add another one. It's a model as well. It's a very high energetic jet, estimated nearby to us. But however, the peak of frequency remains in low frequency, of course. And here I show different components of the jet just for be sure which part is provide the most radiation. Of course, is the jet. The jet provide the more signal, and the cocoon, which is the more slower part, produce less. And yes, my conclusion is basically the most important is from this kind of signals could be possible to observe the main properties of the jet at the first seconds of propagation. And thank you very much for your attention.
Thank you.
Thanks.
Are there any questions? Yep. I might be quickest here.
Thank you for the very nice talk. So it looked to me like your preliminary models of the high frequency signal showed much lower amplitudes than what Gottlieb et al. Have claimed.
Yes.
And I actually think you're absolutely right. I think that their models are insane because they claim that microturbulence somehow magically adds coherently to give you strong, large-scale gravitational wave signals. So I'm curious whether you have any thoughts about why your results are so different from theirs.
Yes, the first one that in his work is used the quadrupole estimation, which is probably wrong because it is made by slow velocities and it's made in the context of supernova. For high densities and slow velocities. And the second one, the jets in this work are produced with very high energy, are very, very energetic. They have cocoons of 10 to 53 ergs, and we never observed that on Jervis. But as it's very energetic, the approximation is overestimated. Here is different. Our is different because it's we take this solution for high for faster material, but and it's basically the difference. Thank you.
Okay, are there any other questions? Maybe questions with the microphone? Any others?
Hey, thanks for that talk. Just a quick question. I think in slide 12, you had 3 moles with an injection time of 10 seconds, an energy of 10 to the 51, and all 3 had a different outcome.
Yeah.
Were these 3 different progenitors, or was it just random chaotic effects of initializing the same progenitor with slightly different numerical properties?
No, we run a set of parameters, just changing the time and energies.
But are there extra parameters? It's just that I think I read the same. You had the same outcome for it.
And in the beginning?
In slide 12. Maybe I misread it.
Here?
No, the next one. That's the one that had the table. Slide 12. Go one more. Slide 12. There. The table. That one.
Yeah.
So you have three simulations with an injection time of 10 seconds, an energy of 10 to the 51, and different outcomes.
Yeah.
So I was just wondering, are those different progenitors that you use, or is
No, it's the same. It's the same star progenitor, and the injection only is. I am injecting the jet by different times, but with different luminosity. This is the final energy. At the final energy at 10 seconds, 2.5.
Okay, so there's an extra parameter that differentiates them.
Yeah.
Okay, thanks.
And the failed jet is we change the jet opening angle just for to lose the collimation of the jet. To lose the collimation, the material is spread and you produce this failed jet. And the supernova is just a thermal pump, a spherical pump.
Yeah, I guess if the angle is too wide, it's essentially
exactly. Yes.
Okay, thank you.
Thank you.
Okay. I don't see any more questions, so let's thank Gerardo again.
Thank you.
And the next talk is by Surajit Kalija. Yep, he's coming up. He's going to talk about the detection of continuous gravitational waves from fast radio burst sites to understand their progenitor mechanisms. The floor is yours.
Thank you very much. So I'm Surajit. I'm a postdoc at University of Cape Town, and this work I'm going to discuss some possible linkage between gravitational waves and fast radio bursts. And this one I have done with Amanda Weltman of University of Cape Town. So because it's a first talk in this session about fast radio bursts, I'm going to give one slide of introduction. So fast radio bursts are radio transient events, and they are observed for very less amount of time. They are very transient, or generally of the order of milliseconds. And their frequency range is of the order of, so far, whatever observed, around 300 megahertz to 8 gigahertz. And they are very bright in radio sky, so their observed flux density is about Jansky order. And the most important distinguish is basically some of them are observed to be repeating, and some apparently not. That means once a burst. Although some of them are observed repeating, there is not any periodic repetition. They might be aperiodic. And they are mostly extragalactic because of their observed high dispersion measures, except one of them, which is related to a magnetospheric soft gamma repeater in our galaxy. But otherwise, most of them are, almost all of them are extragalactic. And so far, nearly 700 of FRBs have been observed. Out of these, most of them are by Chime Radio Telescope in Canada very recently. But the expected rate is around 100 to thousands of them per day in the whole sky, but we don't have enough sky coverage and enough sensitivity. So we are still limited to this number. And so far, lots of theories have been proposed. I'm going to discuss one of them in detail, but there are many theories that have been proposed how these FRBs have been generated. And with these FRBs, because they are cosmological, one of the very few astronomical objects which observed at cosmological distances, they have been used to detect, to understand lots of fundamental parameters like Hubble constant, photon mass, fine structure constant, and so on. So this is the first FRB that's been discovered by Lorimer et al., and they got Shaw Prize last year because of this discovery. And probably you have heard one of their talks a couple of days ago. So if I now come to the FRB progenitor theories, as I'm going to focus only on this aspect of FRBs in this talk. So in general, whatever FRB progenitor theories have been proposed, they can be classified majorly in two categories. One is coming from merger of two compact objects, and another is some physical mechanism happening only in the isolated compact objects. So generally what happens in merger of compact objects, material starts shattered, and it's basically interact with the magnetosphere of these pulsars or the surroundings, and this basically gives a shock emission, and its energetics is such that we see as an FRBs. But in this talk, basically, I'm going to show you some linkage of gravitational wave, possible linkage of gravitational wave. So generally, there are two possibilities that either merger of these compact objects will give a black hole if some black hole merger, or it might give neutron star or white dwarf as the final object. So generally, if we have a black hole as the final object, after it's ring down, we don't see any major gravitational waves. But if final object is white dwarf or neutron star, it might emit gravitational wave, and I'm going to show you how. So in this talk, I'm not going to discuss about this merger mechanism, but I will discuss on these isolated objects, but one of them only. So if we now go to isolated compact objects, in general, there's a basic one that any isolated compact object, if it's behaving like a pulsar, that means it has a magnetic field axis and a rotation axis, and it's being separated by an angle chi, then such an object, because of its time-varying quadrupolar nature, it can emit gravitational radiation. And if you just do some calculation, we can get the two modes of polarization, plus and cross. And you can see both, they are basically a combination of two frequencies. One is rotation frequencies of this pulsar, and another is twice of that. And depends which one is dominating, depends on this pulsar angle chi. And these are all other like components which is related to the quadrupolar moment or moment of inertia. So once we have this, if now we want to detect the signal to noise ratio of this continuous gravitational wave signal, this you need to take into account both this component. You basically need to add the power, and you can see the signal to noise ratio is proportional to this time of data collection of data. So its signal to noise ratio increases as the detection time increases. So with this idea, let's go to one of the mechanisms that I'm going to discuss. So here, there's a pulsar, its pulsar magnetosphere or light cylinder, and this green gravitational wave is basically emitted due to pulsar mechanism that I've shown in the previous slide. Now, suppose there is separate gravitational wave not related to this. It's passing through this magnetosphere. Because of the interaction between this incoming gravitational wave and the magnetic field of the pulsar, one can show that some of its energy can be converted to electromagnetic radiation. So this particular phenomena, which is basically converting gravitational wave to electromagnetic radiation through magnetic field, it has a name called Garsten-Zeldovich effect. So if we just discuss just in one slide of simple maths without detailing, so gravitational wave in fall has two modes of polarization, and it has a frequency of omega g, and rotation frequency of this pulsar is omega rotation. Then you need to just do some Maxwell equation in curved spacetime. And finally, you can show that the output electromagnetic wave, this blue wave, has a frequency which is combination of incoming gravitational wave and the rotation frequency of the pulsar. So if now let's think about what will be the nature of this infall gravitational wave. So FRBs have been observed in megahertz to gigahertz frequency. So this blue radiation has megahertz to gigahertz frequency. Green gravitational wave that is related to the pulsar mechanism cannot exceed more than kilohertz because it's a neutron, at best can be neutron star or white dwarf. So so its range is around hertz to megahertz. So if we now add, and this from this relation, omega plus minus, you can see that omega g has to be of the order of megahertz to gigahertz frequencies. So such gravitational wave cannot be emitted by astrophysical, we all know. And there are many other different mechanisms that's been proposed, like primordial related primordial mass black hole or some early universe cosmology. So there's a nice review where you can see different kinds of gravitational wave which emitting ultra-high frequency range of around gigahertz frequency or even more. So now let's consider one of the examples. For example, let's take this particular FRB, which has been observed in this. These are some observed parameter. Now we have a pulse width. This is one of the highest pulse width FRB that has been observed. So I chose this one. So the pulse width of this blue radiation, this electromagnetic radiation, which is FRB, is basically the time required to cross this light cylinder. And this gives a rough, I shouldn't write equal, it's approximate to the radius of this light cylinder. And if we get the radius of the light cylinder, we can obtain the rotation frequency of this pulsar. And from the theory, we know the flux of this wave, and we know all other quantities. So only unknown quantities left is the amplitude of this incoming gravitational wave and the magnetic field of the pulsar. So we don't know these two quantities, so you need to assume one of these. Of course, this incoming gravitational wave can have amplitude of this high as well as shown by that review paper. So if we assume the amplitude, we get the magnetic field of this pulsar. Now with this rotation number and this magnetic field, one can show that this can possess by both a neutron star as well as a white dwarf. So we consider both this both of these categories, and we now want to model this object. And because it has magnetic field and rotation, and this is an axisymmetric system, you need some kind of simulation. So I use one simulation called XNS. So it basically gives MHD state magnetohydrostatic equilibrium of any compact objects once you put magnetic field or rotation with stable amount. So once we get the structure of this compact object, they look like this kind of objects. I just exaggerated with very high magnetic fields. So you can show that shape is changing, and eventually it can give those quadrupolar moments. So now let's go now once we get the structure of this object, that means its moment of inertia and the quadrupolar moments, one can fit in the gravitational wave equation and calculate the signal to noise ratio that I showed in a few slides ago. And you can show that for different gravitational wave detectors, because this particular FRB's frequency range is coming less than 1 Hz frequency. I just took these detectors, LISA, DESIGO, and BBO. And you can see if it's a white dwarf, it can be detected by a couple of detectors, but if it's neutron star, no detectors can detect. And of course, we don't know the distance of this object, so you can take megaparsec to almost gigaparsec distance. And depending on that, detection time will increase. So some of this, for example, you can see LISA can never detect because detection time requires a very huge number. So another, a second example I want to give, this has a pulse width very small. And once we do, again, all this calculation, one can show that its rotation frequency is high, so it cannot be a white dwarf, but it should be a neutron star. But depending on its magnetic, you choose this quantity again, A+, and you can show that depending on this A+, it can be either an ordinary neutron star or a magnetar. So depending on whether it's an ordinary neutron star or a magnetar, the signal to noise ratio again. So if it's an ordinary neutron star, no detectors can detect, at least within 1 year of integration period. But if it's a magnetar, you can see Einstein telescope or Cosmic Explorer can detect it within 1 year of integration period. So this gives to my summary slide that this particular gravity Gersten-Zeldovich effect can explain FRBs, which both repeating and non-repeating. And so far with the current radio facilities, we cannot distinguish between it's very difficult to distinguish between or rule out some of the theories for FRBs, or many of them, in fact. And gravitational wave observations, I just showed example, but of course, other multi-messengers of other wavelengths or neutrino detection of FRB site from FRB site can detect between different mechanisms, either progenitor or merger versus isolated or some other mechanisms. And also it can infer whether the type of the object is a white dwarf, neutron star, or black hole. And of course, in future, many other many more FRBs will be detected from different like CHORD or HIREX or DSN. So this will give a better picture of the progenitor mechanisms of FRBs. So I'll end here, and this is the published paper based on which this is my talk. And thank you.
Thank you. Before we get to question, the next speaker, Massimiliano Razzano, is he ready and mic'd up? All good. All right. So questions for Surajit. I see 2 hands. Yeah, I'll run up here. Okay, you're quicker.
Thank you. So I'm trying to understand the overall energetics. How does the energy incident from the gravitational wave, the original gravitational wave, on your FRB progenitor compare with the net energy output in the radio burst?
Yes. So if you take the energy, so incident gravitational wave will have some energy. Now magnetic field will transform it to electromagnetic radiation. Now, depending on the strength of the magnetic field, you can show that the energetics of the output electromagnetic wave will have different energy. So if it's a magnetar or a neutron star, so eventually that basically gives rise to whether it will be an FRB or a less energetic radio event. So the magnetic field of the pulsar will be responsible in the observed energy of the FRBs in this mechanism. No, there will be decrease. It's always a fraction of the incident gravitational wave.
Other questions? Yep, there's 2 up there. Yep.
Yeah, in your summary, you said that the current radio observations don't distinguish between the models. Do you have some observations in mind that might help?
So one is, of course, our galactic FRB, which has been detected, and it's been confirmed that it's associated with a soft gamma repeater, which is a magnetar. So for that one, definitely this is coming from magnetar. But for the other ones, which are extragalactic, it's very difficult. So far, we don't know any of them. So there has been tried to detect some neutrinos or basically in South Africa, we have an optical telescope called Meerlicht, which is supposed to observe FRB after Meerkat observe in radio. So Meerlicht is an optical. So if they see something, then only we can say something about FR progenitor mechanisms.
Okay, we also have a question online, and then one more in the room after.
Hi, thank you for this very interesting take on the FRBs. I was just wondering that most FRBs have a broadband spectrum. That means in the radio regime, you see the emission across a large band of frequencies. So is there a mechanism by which this GZ effect would produce a spectrum for the radio emission?
I don't
and
think
what would be the
GZ,
background spectrum?
Okay, I don't think GZ effect can give a broad spectrum because final emission, unless the incident gravitational wave also has a spectrum, say from the incident gravitational wave has a spectrum, then the output electromagnetic wave will also have a similar thing. But if incident gravitational wave is like a single band or so, then the output should have only one frequency also, or a very close frequency.
But the FRBs have a large emission over a large band of frequencies.
But the peak frequency is generally observed at certain wavelength, right? Certain frequency. So I'm just taking the peak frequencies in this case.
Okay.
Okay, we have one more question in the room, and then we should move on. Yeah, please.
Thank you for the talk. And so I would like to know what could be the possible timescale between the detection of the gravitational wave and the FRB. And second, I would like But so the LVK is already active. So is there any example where the LVK is active and detected something, and there is a simultaneous observation of the FRB?
See, if it's coming from a merger event, so it should be like simultaneous observation, like very quickly, like we have GW17 where GRB is observed. But if this mechanism is responsible, it's emitting gravitational wave even after FRB phenomena is done. So object is still emitting continuous gravitational wave in future. So that probably can be detected in the future by detectors. And sorry, what's your other question?
Second question is there any example where the LVK was active and looking, getting some gravitational wave, and there is a simultaneously FRB detection?
So far I don't know, except I saw only one paper where they claim of one-time FRB, which is related to this, came last year. So apart from this, I don't know any other confirmed detection.
Okay, thanks.
All right, we should move on. Feel free to talk after in the coffee session. All right, let's thank Surajit again. Okay, we're moving on now to ground-based instrumentation. And the next talk is on the low-frequency frontier by Massimiliano Razzado. The floor is yours.
Thank you. Okay, good afternoon, everyone. So today I'm going to talk about a new concept for a seismic attenuation system that we hope it will be enabling the low frequencies for gravitational waves. And this is not just my work, of course. You can see the team here that is working with me in Pisa on this new idea. Okay, so first of all, I'm sure you've seen this picture many times, so this is just to put the things in context. So these are all the second generation detectors that we have, like in Virgo. And of course, you know, there are projects for the third generation detectors. So when we are studying the sensitivity of the detector, it's important to remember that this is the sensitivity curve. And you see that more or less are similar. And it's important to study the noises. So at lower frequencies, we are dominated by the seismic noise, the so-called Newtonian noise as well, so gravity fluctuations. In the mid regime, we are dominated by thermal noise, and the higher frequencies, we are dominated by all the quantum noise. For example, the quantum fluctuation related to the lasers. So we'll be focusing on this low end of the gravitational wave frequencies, and in particular, this is very important. We have discussed this already in many talks. So low frequencies are very important. For example, when we want to study high mass black holes, for example, you can see that, of course, with the Einstein telescope, you can see that we will be able to go up to very high redshifts. And the largest the mass of the black hole is, the lower is the frequency. So if you go to lower frequencies, you are expected to see higher mass black hole. In particular, for example, also the intermediate mass black hole. And also, we are expected to see black holes very far if we are going to low frequency. So this is just an example of the science case that we can access with low frequencies. Of course, also all the transient events related to the dynamical captures are focused and are basically located at lower frequencies. Another important science case is related to the binary neutron stars, because if we are able to see the lower frequencies, we are able to enabling early alert for these events. And of course, this will enable multi-messenger observations. So for example, here you can see that if we move from a frequency threshold of 30 Hertz down to 10 Hertz, we are able to see our signal much earlier. So from, let's say, 50 seconds up to 15 minutes, 16 minutes. So this means that we will be able to do a pre-alert, issue a pre-alert much in advance, so that we can tell telescopes so that they can point to the event. And there are other science cases. I will not go beyond it in details, but for example, pulsars, we have just heard about continuous emission. So we are expected to see continuous emission from pulsars, and these will be focused and it will be also concentrated at lower frequencies. So when we are talking about how to enable these low frequencies, it's important to study and to see what is the sensitivity curve expected, for example, here in this case for the Einstein telescope. As you know, the Einstein telescope will be composed according to the current projects by two interferometers. One is focused on low frequencies. that you can see here, and another one that is optimized for higher frequencies. And when we look at the detail of the noise budget here, you can see that around 2 Hertz, there is the crossing point between the Newtonian noise and the seismic noise. So if you want to study a system to attenuate the seismic noise, you should be considering this point as a, let's say, as a reference. And today, the baseline configuration for the seismic attenuation in the Einstein telescope is an evolution of what we have in Virgo, the so-called super attenuators, but very high, like 16 meters high. Of course, if we can do something that is more compact, we will, of course, reduce all the excavation costs and make something that is simpler. And this is what I'm gonna tell you. But before telling our idea, I'd like to just recap the idea of the seismic attenuation system of Virgo and the one that is proposed for AT, which is the super attenuator. So the idea is to have these very complex electromechanical devices where you have a passive attenuation given by this chain of pendulums, and then active attenuation by a system of active controls. Currently, you have basically 3 elements. You have a pre-attenuator, which is a 3-legged inverted pendulum. Then you have a set of mechanical filters, a set of pendula, and then you have these final components, which is called the payload, which basically means the mirror and the so-called marionette that gives you the possibility of orientating these mirrors. So the total height is in Virgo, for example, is about 9 meters, and for ET will be much higher. And if you look at the attenuation, you can see that we have a very large attenuation, and this is mostly given by passive attenuation of the super attenuator. And if we go more in details, you can see these 3-legged inverted pendulum. On top, you can see this what we call the filter 0. So it's a mechanical filter on the top. And the idea is that if you recap the physics of the inverted pendulum, is that we have this inverted pendulum in order to have something that is very, very soft. So that you can move it with a very tiny force. So you can basically control very easily. And of course, you can adjust by changing the masses and the length. You can adjust the resonant frequency. So for example, in this case, for Virgo, we have a resonant normal modes around 30, 40 millihertz. And this is one important component that is acting as a pre-isolator. Then you have the mechanical filters, the standard filters. Here you can see the two examples. So a mechanical filter is basically a complex, let's say, rigid body, which is composed by 2 main components that are able not just to oscillating in this direction, but also in the vertical direction, because we also want to have a vertical attenuation. And that's because of the fact that the Earth is curved. So if a mirror moves in the vertical direction, these also will change the relative position. And so you want that the 2 mirrors will be exactly maintained at the very same position. So that's why we implemented this vertical attenuation with a system of cantilever blades. These are here. This is a mechanical system, and then you have a anti-spring, magnetic anti-spring. And in this way, you can basically fine-tune the resonance, the vertical resonance of your system. So let's move to our idea. So the idea is that we want to make something that is working as the super attenuator, but it's more compact. And we came out with this idea of a system that is composed, basically, instead of having a single standard filter, we have a combination of an inverted, mean inverted pendulum and a suspended mass. So we call this pendulum inverted pendulum. So here you can see some numbers, and basically what we have done is to start our calculations, and we basically shown that this system can be made mechanically stable if you select the stiffness of this flex joint, that is basically the base of your inverted pendulum, and if you can make it stiff, this system can be stable. So the idea is to replace one standard filter with a system like this. And in this way, what you also can demonstrate is that you can achieve the attenuation factor of 2 standard filters in the space of 1. So the idea is that using this system, you can make an attenuator that is more compact, at least by a factor of 2. And then, of course, you can adjust the numbers. Here, this is just a first set of calculations. So here is a more, let's say, detailed example. Here you can see a CAD drawing of the real pendulum inverted pendulum. So you can see that we have still a 3 leg, like in the big inverted pendulum. And on top of that, you have some masses. And the idea is that these things you will suspend. And from this, you can suspend another pendulum inverted pendulum. So the attenuation factor, as I was mentioning, is this one. So this is basically the equivalent of 2 standard filters, but again, is in the space of 1. So we can do some calculations. And for example, the required attenuation that is required after you consider the full inverted pendulum and the payload, it's in the order of 10 to minus 5, and you can achieve this with 2 or at maximum of 3 inverted pendulum. So what we have done these simulations, calculations. Now we are working on that. We are working on creating the first prototype. So here, for example, you see one of the legs of the inverted pendulum, and we are working now on studying the transfer function to be able to see that these things is actually working in the lab, not just on the simulations. So we are doing some measurement of the transfer function. So for example, here you see that as expected, the resonances is changing when you change the mass here at the bottom of the legs, and this is an example of how you can fine tune your inverted pendulum to have the frequency that you want, the resonant frequency that you want, and this is where we are, but of course now we are doing other steps. So here you can see the 3 legs. So just to conclude, we are proposing this new concept, and you can see here we have an example of this 3-legged inverted pendulum. So what we aim is that, of course, the system could be a possible option to enable the lower frequencies sensitivity, and this, as I said at the beginning, this will help in many different science cases. For example, IMAS black hole, multi-messenger, so early warning, other sources like pulsars, etc. So the idea of this component is to implement a passive and active attenuation factor. So not just the single passive attenuation, but also we can control it. We haven't done yet, but we're working on that. And just to remind, this project has been supported by a project that has been founded by the Italian government. We are basically doing the construction and the first test in the lab. And as I mentioned, we're not just doing simulations, but here is our first prototype. And the next step will be to suspend and to test these things under more realistic conditions. And that's all for me. So thank you very much.
Thank you. Questions from Massimiliano? Yep, there's one.
Hi, Massimiliano. Thank you. That's a very interesting technical development. I was wondering, when you couple multiple of these inverted pendulums together, how does the length of the wire that you attach from the one to the other, how does that affect the overall attenuation? Could you pack them very close together vertically, or do you need some minimum length of the pendulum for the next one?
So yeah, this is a very interesting question. We are thinking about it because depending on how you packed, you can have different attenuation. One key point that we haven't studied yet, because we are preparing our first prototype, is that here, when from here you can suspend another mass, and in between 2 inverted pendulum, you can insert a stage like a standard filter that can provide vertical attenuation. So this is a key point that we will address. And yes, of course, depending on this, the full attenuation factor, especially also on the vertical part, will change. But yeah, we are studying this.
Any other questions? Yep, there's one there. Microphone is coming.
Thank you for the very interesting talk. This is completely not my field, but within the same packing or the same space currently planned, how many can you put in the same space? And then how much does that reduce your seismic noise down?
Yeah, so the idea now is that instead of having something like 70 meters, well, we can have something in the order of, let's say, 8 meters, something, depending whether you use 2 or 3 of this system. Depending 2 or 3 depends on the frequencies, because the frequencies has an impact on the attenuation. So we are now working on the data calculation to find the optimal way. But let's say two or 3, so a factor of a half at least in terms of height.
Okay, cool.
Thank you.
Other questions? I actually have also one. I'm wondering whether you have any issues with internal modes on the inverted pendulum that might affect your high frequency isolation.
Yes, this is something that we are studying right now in these days. In particular, we expect to see this when we will suspend. So in particular, the coupling, the tilt coupling could be something but we are studying right now. So far, we are making this thing that is stable and adjusting you see here the counterweights. So yes, this is something that also needs to study.
Looks very interesting. All right, any other questions? If not, I think you all earned a coffee. Thank you. You can start.
Okay, I think we'll get started in just a moment, but there was an announcement before the talks began. So if we could put up the one slide. Yeah. Yeah, so there is one slide to show at the beginning. If you could please put that up.
Hi, everyone. So on behalf of the IAU Working Group on Global Coordination of Ground and Space-Based Astrophysics, I wanted just to highlight for you that will be around next week that we have a session next Wednesday from 10:30 to midday, where we'll be focusing on what's required in terms of ground and space-based facilities for transients and in particular for follow-up of gravitational wave and other astroparticle events. And so I would really like to welcome and encourage you all to attend, because we will also be able to provide the IAU with a report as well as recommendations. So please do, if you're still around, do attend next Wednesday. We'll have three talks as well as a panel discussion. So lots of opportunity for input, or you can also just email me or Varun Balero, who I'm co-organizing this session with, just with anything you'd like to raise or bring up. Okay, thank you.
Okay, and our first speaker is Stefan Ballmer.
Thank you. How's the microphone? Excellent. So now we just need the slides and we'll be ready to go. Maybe I can get started. First of all, thank you for inviting me. It's a pleasure to come here. It's my first time down here. I'm really enjoying myself. All right. So I'm going to be talking to you about the future of gravitational wave ground-based detectors. In particular, I'm going to focus most on the Cosmic Explorer project, of which you see that the graphic in the background, because that's what I'm actively working on. So I know the most about it. All right, so quick overview. I'm going to start with what LIGO is doing, how it's doing from an instrumental side, and what that means for us designing the next generation of observatories. We'll look at what we can do with those, and then look a little at timelines and decision trees and what we need to do to get there. All right, so you've probably all heard the LIGO observatories have been working quite marvelously at around 160 megaparsec binary neutron star and spiral range. Here are the gravitational wave amplitude spectral density plots of the two instruments. These are the usual plots where we're plotting this strain over square root hertz as a function of frequency. So square it, integrate it across your band, square root of it if you want to know what the strain noise is in a certain band. And you can see these things are limited by at about 10 to the minus 23 strain per root hertz over a big part of the band. The low frequency here is a whole bunch of ways how seismic noise coupled. That was the previous talk, how you can fix that. At the high frequency here, it's quantum noise. And in the mid frequency here, we have some thermal noise breathing in. In fact, going into the 04 run, the big upgrade we had was what we call frequency independent squeezing, which is really below standard quantum noise detection of our gravitational wave channel. And so I'll walk you quickly across these plots. These, first of all, are two sort of twin plots, one for the Hanford instrument, one for the Livingston instrument. Pick your favorite instrument. The information is basically the same. It worked in both. In black on both, you see the sensitivity of the instruments if you just bring in the laser and read it out, no quantum matching involved. You find that your shot noise limited above about 100 hertz.
And at low frequency, you have other noise sources. You don't see the radiation pressure noise dominating that curve, but it's not far below the classical low frequency noise. Now, if you then turn on squeeze light and inject it from the dark port in the interferometer, you immediately improve the shot noise at high frequency. But the Heisenberg uncertainty principle says that the other quadrature is getting worse, and it's actually getting worse more than the Heisenberg uncertainty principle tells you, because this is a real experiment. You always do worse than the minimum. And so what happens is the radiation pressure noise actually shoots up significantly if you do that, to the point where in previous round we couldn't actually inject our maximum squeezing because we just would have wasted the low frequency sensitivity. We then constructed a filter cavity, 300-meter long optical cavity, whose sole purpose is to store that quantum state of light for the right amount of time to rotate the relative phasing. So we're now no longer sensing that increased quadrature, but rather the other lower noise quadrature in the radiation pressure regime. And that resulted in the purple curve, which is now improving the black curve everywhere above basically about 50 hertz or so. So everywhere above 50 hertz, we're getting a benefit from using below quantum limited sensing. And so these are just a few pictures of that cavity construction that happened the last few years. Correct me if I'm wrong, but I believe that's still the most concrete port to store a quantum state. But I find it kind of impressive the extent we go to just store a quantum state. All right, so the result of that is that O4A here went pretty marvelously from a LIGO perspective. The event rate was, as predicted, kicked up by the expected notch that you get from that increased sensitivity. And since this is an experimental talk, I won't dive into the details of the events that we're seeing. In fact, that's an older plot. Sylvia's talk from yesterday, I guess, went into much more of the recent news. Instead, what I'm going to do is I'm going to zoom in on one event that is close to my heart for a technical reason. And that's this 1904-12 unequal mass binary. That was the first time we saw higher order modes of gravitational waves emitted by that source. Why is that interesting? What that meant is because we had the sensitivity to see those, we could get the information in those modes to reduce the uncertainty on what's otherwise a degenerate situation between the luminosity distance we infer and the inclination angle. But seeing these higher order modes actually breaks that. And so as a result, if you get the sensitivity of the next generation higher, you can actually expect better parameter estimation of distances, inclination angles, etc., than what you naively would expect. So I'll leave it at that. Just one more slide on what's going to happen in the upcoming. So right now, actually, one thing I don't have a slide, the Hanford detector is now currently down. It had an issue with a damaged Faraday isolator, which is being fixed. It just takes time to pump it down again. So it's off for 3 weeks now. Hopefully it will be on again soon. Then after the 04 run, there's a couple of upgrades planned. We still plan to get better optical coatings in there, which should reduce that thermal noise in the middle of the band a bit, get it out of the way. And then finally, there's a sensing change where we want to switch from a offset locking to a balanced homodyne readout that in principle should reduce some technical noises. And we're still very close to clipping in our beam splitter, so that we finally decided to also fix that. So that's the status of advanced LIGA. We have seen about 150 sources so far. We're getting a really good idea of where we are. So that begs the question, what can you do next? Given that we know what source population is out there, we know what worked, what didn't in the detector construction, what should we do next? And what does that next generation promise us? And so that's what the rest of this talk is about. On the world, there's currently 2 projects that aim to do that. One is the European Einstein Telescope. It's an underground facility with 10-kilometer arms. There is 2 sites proposed. And the other one is the US Cosmic Explorer. It's a surface-based, 2 L shapes. Proposed is a 40-kilometer and a 20-kilometer. And I'm going to be mostly talking about the Cosmic Explorer, just because that's the one I'm working on. But many things of the science case and even technical issues are really transferable between the 2. So I'll leave it at that. Okay. All right. So Cosmic Explorer, as I said, 2 machines, just like LIGO. The difference is we'd like them to be arranged differently, so they're sensing both polarization. Advanced LIGO was actually aligned to sense the same polarization, which is an advantage if you want to prove that you detect the gravitational wave, but it's a disadvantage if you want to get all possible information about an inspiral event. So that's one change. We are aiming for roughly 10 times the sensitivity, and we'd like to operate in a network. Again, that's for getting the most benefit science-wise out of it in terms of triangulation, localization, and follow-up. The science case really has 3 highlights. There's many details behind that, but I think sort of the top 3 things is with these next generation detectors, we're taking gravitational wave observation throughout the cosmos right before the first star forms. So if there were black hole mergers before there were stars, we would see them. The second is looking at the dynamics of dense matter. So that's looking at the nearby sources, the ones we've already seen, but just 1,000 times better signal to noise. Really understand what's happening with dense nuclear matter. And the last one is similarly a high regime measurement of extreme gravity, precision measurement of gravitational wave forms. All right, so this is just a slide to point you to the right direction for the webpage, cosmicexplorer.org, if you want to follow up on it. One thing you find on there is that Horizon study that we published now almost 3 years ago, which just lays out the concept of Cosmic Explorer, what we think it can do, what the challenges are. So if you're interested, feel free to take a look. Cosmic Explorer right now is a couple of institutions involved in it. We're collaborating on this. It's more than just the LIGO lab, but the LIGO lab is also involved because a lot of expertise obviously immediately transfers. All right, so what can we do with this instrument? So this is a graph that we put together where we have on the x-axis just the total binary mass of a typical black hole or neutron star binary. And on the y-axis, we just have the redshift. And then on this y-axis, there's a time and some cartoon to just give you a little context what else is happening in the universe at that time. Plotted here is the Cosmic Explorer 40-kilometer detector sensitivity with a detection signal-to-noise ratio of 8, which is sort of a standard in the field to gain confidence in the signal. How far you can reach. And right here you see for total mass of about 10, we're reaching to further than about a redshift of 100, which really will go beyond those first stars. Next, I'm also plotting the same signal-to-noise curves for the same detector, except for a signal-to-noise ratio of 100 and 1,000. So sources that lay within this envelope, you will see with a signal-to-noise ratio of 1,000. So there's highly defined waveforms where you can do precision measurements on it. Superimposed here are the current sources, at least at the time we had the plot, where the LIGO sources actually lie. And you can see almost all of them are right around the SNR of 1,000 range. So all the sources we see now, Cosmic Explorer would see plus or minus an SNR, signal-to-noise ratio of 1,000. You can then take these sources, extrapolate from based what you know about the universe, where you'd expect the bulk of these sources to lie, given the stellar evolution modeling. And you'll see that the bulk of all black holes will certainly be in range of that detector. Most of the neutron stars, that will also be the case. We'll see most of the neutron stars in the universe. So in other words, the detection rate for Cosmic Explorer is no longer sensitivity limited. It's really limited by the size of the universe. The other thing worth mentioning here is, as you know, we've seen many, many more black holes than neutron stars. And that's really just a selection effect from the fact that this curve is so steep. And we see very much fewer neutron stars than black holes. But once you're in that next generation, that actually reverses. You basically see all the events in the universe, and you'll actually see more neutron stars than black holes merging. Okay, couple of more things superimposed here. Known gamma ray bursts, redshifts are all in band, so they sort of superimpose. We put them here, assuming that they are binaries. Of course, there are other ones that are not binaries, but okay. Population 3 black holes from the very first star. They tend to be heavier, so they would show up somewhere here. So we could definitely map out that population if it exists. And then finally, maybe more speculative, if there are any primordial black holes that have nothing to do with stellar evolution, they would also be in the maximum range of these detectors. And the very last thing on the plot, because we're building a new facility, rather than just taking the detector sensitivity, I also projected what's the limit of the facility that we want to build. And you can see that at heavier masses, we're really running into the seismic noise on the ground. That's why this is dropping out. So that's not a question of how well you can sense it. It's just the foreground you face on the ground. And even if Massimo does a fantastic job with his isolation, you will still get the Newtonian shortening out of the Newtonian of the seismic noise, basically ground motion coupling through Newtonian gravity to your test mass, shorting out your isolation system is really what limits you here. On the high frequency, it'll be the quality of the vacuum, basically the residual gas in your vacuum tube that limits you. Okay. So on the next science case for neutron stars, what I've plotted, what you see in this plot here is really a phase diagram for nuclear matter density versus temperature. And you can think of a binary in spiral as performing a walk through that diagram, first at a low temperature during the in-spiral phase through measurement of the tidal deformation. You can measure the property of the behavior of the nuclear matter here. Then as they collide, they heat up, and you get the dynamics in a post-merger waveform as you observe the gravitational waves emitted from the material moving around after the collision heated up, and then it cools down again. So it provides you this walk through that phase diagram of the quark-gluon plasma. And then the last thing I want to highlight is something that I think we've not paid enough attention to so far, and that a one-year data set of these next generation detectors opens up a whole new set of cosmological observation, because you're talking about an order of 1 million neutron stars, an order of a 10 to the 5 black hole mergers per year, up to redshifts of 30, some of them 100. And that by itself is an interesting data set looked at as a whole. So here, I just as a teaser, I put a slide that was actually given to me by Sumit Kumar, where he produced a combined posterior field just from the gravitational waveforms that you get if you have 3 detectors, 3 next generation detectors in the system. And you can see the localization. This is just plotted 2-dimensionally, but you also get the distance, luminosity distance. the resolution is really good enough to see baryon acoustic oscillations just from the distribution of the black hole mergers. So that's just a teaser of the sort of thing you can do with these data sets. All right, so how am I doing with time? Okay, that's perfect. So let me talk a little bit about the detector design itself. So as I mentioned, we recently got initial funding to start the design for Cosmic Explorer. Here's a list of all the activities that are ongoing, management coordinating everything. Maybe the biggest leading item here is just the search for an appropriate sites. That's currently actually funded at the highest level, and it's the highest priority. We need to build this detector somewhere, and it better be at a place where we're welcome. And we can do the science. Other things that are happening is the optical design. I'll say a few words of what's happening here. Changes we want to make compared to current detectors to operate at higher power. And then, as mentioned, ways to mitigate these Newtonian local gravity disturbances, as well as scattered light. There are other hardware efforts, research efforts on the way, in particular vacuum system research, because that's the driving factor. If you're building a 40-kilometer, 1-meter diameter vacuum tube, that's where the money goes. And research on improving the coatings and suspension design. Good, just a slide on the site search. So clearly what you're looking for on a surface detector of that size is something that's flat. And by flat, I don't just mean same elevation. I actually mean flat as our laser beams see it. So really what you want is a slight bowl of the order of diameter of 40 or so kilometer that ideally just compensates the Earth's curvature for you. Now, you'll never get that perfectly, but it turns out there are sedimentary basins of that size that get pretty close to something like that. You probably have to dig some tunnels, but you get pretty close, and it's actually better than you'd think naively to find something flat that big. Clearly, you also want a good seismic environment. There's actually sort of an interesting trade-off. I just mentioned sedimentary basins. Well, they're really acoustic cavities. And so what do? Well, they resonate seismic waves, which actually leads to enhanced microseismic activity at the edge of the basins. And so that shows up on this match. Wherever you have seismic basins, you tend to have elevated microseismic activities, which is certainly something that's good to know. Mind you, one of the LIGO detectors is actually down here at the Gulf Coast, so it's nothing that we can't design around, but it's definitely, we have to be aware of that. And then, as I mentioned, it's really critical to us that wherever we go, we're welcome. This is a detector that we need the local support of the population, indigenous. It'll be an impact economically as well on the area. So this is big part of trying to find that site, that this is something that can flourish. Good. Let me say a few words on the optical design. And so I know this is not really what you usually think about, so let me just point out to the left here, this is the advanced LIGO optical layout, and here is a coarse layout of what we think for Cosmic Explorer, and I'll just go through and point out the main differences. Of course, the arm will be longer. The test masses will go from about 40 kilograms to about 320 kilograms. The arm power, right now, the design arm power is actually similar for A+, the current advanced LIGO, and a Cosmic Explorer, although currently we're about a factor of 3 to 4 lower than that design arm power. However, the power density on the mirrors is exactly as what we're operating right now, because the test masses are also, or the spots are also 4 times the area. we're moving around where the telescopes are. That has to do with the beam splitter, otherwise being the biggest optic, and you don't want this to be the driver. There are considerations how you do the frequency locking, so there'll likely be the requirement for more input mode cleaners. But that's essentially it. So this is, I think, more or less the same list. Make sure I didn't forget anything. Filter cavity will be bigger than what we built now. So think of a few kilometer filter cavity instead of the 300 meter that we built now. But that's essentially the cornerstones of the detector. There are some things to point out that are different if you go to larger scale. And I'll just list 4 of them. First of all, I just mentioned the beam splitter. If you put it on the 45, your optics are already 70 centimeters. You need to be square root of 2 bigger. That tends to make it unpractically big. So if you can find an alternate layout with a smaller, not 45-degree incident on the beam splitter, you can win there. There is a push to keep the signal extraction cavity relatively short. And that has to do with the desire to have a good sensitivity at those post-merger frequencies at a few kilohertz. And so that puts a constraint on how much space you have to put in your telescopes to get that sensitivity right. Also, the longer arm means the signal extraction cavity needs to have a higher finesse. That's actually a good thing. That makes it much easier to control than advanced LIGO, but it's nevertheless a design difference. And then finally, the other thing that's different, because we have that larger cavity, we're now using much more of the cavity-free spectral range as an observation band. So things like higher order modes that currently in advanced LIGO lie outside the observation band end up being in the band. So the result of that is things like thermal compensation have a more important role to play. All right, so these are just through concept. That's more or less the concept I've shown in the previous slide. To address that 45-degree incident, we're looking at layouts like that. We're in the process of working all that out, what works best with all the geometric constraints. So that's work in progress. All right, so just a reminder, the key technology changes, we need to get the larger optics. Coatings are still key, both the thermal noise, but increasingly, for the reason I just mentioned, absorption of the coatings is key. That's also what's limiting advanced LIGO right now, is the optical absorption. Squeezing, it's the dominant noise source across most of the band. Seismic isolation system to get the low frequency, and of course a place to put it in vacuum, so a large vacuum system. This is the predicted sensitivity. You can see we expect to reach a strain sensitivity of, what's that, about 3 × 10⁻25 across a pretty large band, thanks to a good attenuation system at low frequency. The thermal noise dropped because of the length and the size of the optic, and the rest is the suppressed quantum noise. Good. Just a few slides on where we are. So this is a schedule that we essentially put together 3 years ago at the end of the Horizon study. Up to now, it's more or less intact. No big changes. We're now got the design stage initial funding here, so that's ramping up. But you can see pretty soon there will be milestones that are critical, like site selection to stay on course. So that's currently what we're working off. So far, you can't prove we can't do it, but I'm sure there will be some slips somewhere. More recently, the NSF actually organized a subcommittee study where you can see that the links are here, where they asked for input of detector designs that essentially could deliver 10 times the sensitivity of advanced LIGO. We did submit the white paper to that, and that report is now out. This is the web page. You can find all the information there. And essentially, the recommendation from that subcommittee to the NSF is the NSF should go ahead with a Cosmic Explorer detector. For sure, a 40-kilometer detector. And depending whether Einstein telescope goes ahead or not, we might or might not want to build a 20-kilometer detector. And it also highlights the importance of having a third detector somewhere in the world, even if it's a second generation detector, to get the triangulation right. So I think I'm more or less running out of time, so I'll just leave this summary slide there, and I'm happy to take your questions.
Great. Yeah, thank you very much for the very inspiring talk. So we have some time for a couple questions. See one from Ilya.
So as a newly minted Australian, I'll ask an Australian-focused question. Some of my colleagues in Australia are very passionate about the idea of bringing a detector to Australia. How realistic is it that, let's say, some version of Cosmic Explorer with obviously some funding, at least for the insides of the instrument coming from the US, could be built abroad in Australia?
Yes. So let me first, a couple of thoughts. First of all, the NSF is always looking for international collaboration. The way they look at it is, if nobody internationally wants to do the same thing, then we're doing the wrong thing. It's sort of self-confirming in some sense. The other piece, though, that actually highlighted in that report is the importance. They use the LIGO India project as an example of that, as a detector that provides that third leg in the triangulation. And for sure, a third generation Australian detector would do a much better job. So in my ideal world, Australia could build a 20-kilometer CE, or even if it's a 10-kilometer, A-sharp type detector, with it could really make a key difference for that third generation network. So from my point of view, that's an option. Yeah, obviously, we need to get the track and the support for funding something like that in Australia. And scientifically, the case is very strong. The rest is politics and money.
Any other questions? We'll go to the back.
Thank you for this nice overview. Could you tell us a little bit more about what sort of localizations you might be able to get in these various scenarios?
Yes, I don't have a good slide on me. The Horizon study I pointed to, that's a good place to go. There's sort of a table in here that tries to break it down. I can say a few general things. Obviously, you want the baseline, and that helps you a lot. The other thing is, if you want to do follow-up to optical follow-ups, those tend to be sources that tend to be nearby. And so it's actually good enough to have a second detector that's not the same sensitivity to localize nearby sources. So that's where the idea comes in. Even a slightly improved second generation detector could provide you most of the localization you need to follow up nearby sources. That statement is no longer true for the furthest away sources. So if I go back to this sort of posterior that Sumit Kumar produced here, that really relies on having 3 third generation detectors, so you get good localization even on the furthest lowest signal to noise sources. And because the degeneracy involves the luminosity distance, it is important to get that localization also just to know a precise distance to the source. So that's an additional piece to it, where really the network is key for a lot of the science you want to get out. The network is not important for items like tidal deformation, time evolution of the system. So in system physics, there usually one detector with large sensitivity is good enough.
Okay, I will have to leave it at that. So
Okay.
let's thank Stefan again.
Okay.
And if you have the next slides up, please. Yeah, and your microphone is coming up, Maura, and you can go get it in a second. And yeah, our next speaker is Danny Price from the SKA.
Thank you. create the slides, but as they're coming up, here we go. My name's Danny Price, and I'll be giving this talk on behalf of the SKAO Science Operations team. I'd like to start by acknowledging that the SKAO telescope is built at Inyarimana Ilgari Bundara, the CSIRO's Murchison Radio Astronomy Observatory, where we're building the telescope. And I'd like to acknowledge the Wajiri Yamaji people as the traditional owners and native title holders of the land. The other thing I wanted to mention is please check out the art exhibition downstairs, Cosmic Echoes. This is from a previous art exhibition, but there's some great art from Australia and South Africa. Okay, well, I know this is the GW session. I wanted to start by giving an overview of the SKAO telescopes and then talk about how it relates to possible GW discoveries, and then go from there into some tools and opportunities with the SKA. So the SKA is an intergovernmental, or the SKAO is an intergovernmental organization made up of 10 member states and 6 SKAO observers as of June, and 7 African partner countries. Now, the SKA is 2 telescopes and a headquarters. The headquarters is in Jodrell Bank in the UK, and the 2 telescopes, one is being built in Western Australia, where I'm based, and then the other is being built in the Karoo, which is about a 7-hour drive from here in South Africa. Just going through the telescopes a bit, it will give frequency coverage from starting at 50 megahertz all the way up to 15.4 gigahertz. And there's 2 telescopes, SKA low and SKA mid. SKA low uses a very different technology called an aperture array, and SKA mid uses 50-meter dishes, very similar to Meerkat. Now, SKA low will be made up of 512 of these aperture array stations, and each station will have 256 antennas within it. That makes 131,072 of these log periodic antennas that look a little bit like Christmas trees strewn across the Australian outback. The frequency range it covers is from 50 to 350 megahertz, and the longest baseline between stations is 74 kilometers. SKA mid, on the other hand, is using dish technology, and there will be 197 fully steerable dishes. This is 64 of the Meerkat dishes and 133 new dishes made by China's SETC 54. The frequency range the dishes will be operating over is 350 to 15.4 gigahertz, although they are capable of going higher than that. And the maximum distance between dishes is 150 kilometers. They're arranged with a compact core with lots of antennas in, and then 3 spiral arms going out to 150 kilometers. In terms of receivers, to start with, we'll have 4 receivers available on the telescope, going from 350 megahertz all the way up to 15.4 gigahertz. And these are called Band 1, Band 2, and Band 5. Now, this is essentially just a big bunch of numbers, but the idea of this slide is to convince you SKA is an ambitious project. It's a large project, and the exciting part is that this is underway, and both telescopes are well in development. So I'll take you through that now. So to do that, I'll go through the timeline and something we're calling the stage delivery. So at the moment, we're working towards something called AA.5, which we're calling a milestone event. And the idea is that essentially every year or so, we're going to release another release of the telescope with more stations within each one. So AA.5, we're working toward 4 dishes up and working, when 4 stations up and working on SKA low by the end of the year. Next year, we'll be working on AA1, which is going to 8 dishes, 18 stations. And by the time we get to AA2, which is currently the milestone is in 2027 May and 2026 October, respectively, that will have 64 dishes and 64 stations. And this is where really, firstly, it will become available to the science community through the verification process, but also it's where it really becomes a scientifically competitive telescope compared to other telescopes out there. Now, we're currently funded up to something we're calling AA star, meaning that this is fully costed and the construction is underway to this point. That will have 144 dishes and 307 stations. The baseline design, AA4, as it is now known, We still have a firm intent to build out AA4 to the full design. However, we're focusing on getting to science as early as we can with the funds we've already got fully costed for, and that is AA Star. I'd like to give you a few construction highlights to start with. Firstly, for SKA Low, we have completed building the first 2 stations in May 2024. And as soon as we turned those on, the telemetry started flowing and we're able to see things like the station band passes. And this is a really big milestone. So those 2 telescopes are now working. We've got the other 2 that we're bringing online. And similarly, here in South Africa, the big lift happened in the 4th of July on Independence Day, where we lifted the reflector onto the pedestal, which marks, the first SK mid antenna being built. Getting into the gravitational wave astronomy with the SKA, if you go back to 2014, there was a large book where we got a lot of different science cases written up based on the baseline design, and Jansen et al. Put together a science case for gravitational wave astronomy with the SKA. And I just wanted to mention one sentence from that, which is, with the SKA as described in the baseline design document, it'll have a 50% probability of detecting a GW source after 5 years. Now, if you heard, for example, Ryan Shannon's plenary talk, Meerkat, which has 64 antennas as opposed to 197, but very similar technology, was able to get to a pretty convincing looking detection, to me at least, within 4 years. So it's likely that the numbers here are a little bit out of date. And indeed, a lot has happened in FRBs and pulsars in the last 10 years. So this gravitational wave science case is now 10 years old. And given the progress we've seen in pulsar timing arrays, which is incredibly exciting, as well as some of the changes to the SKA design, the forecasts are out of date, and we need the community here to help us update that. I think the main relevant changes, just to highlight them, is that the band 3 receiver will not be installed initially. And we are working toward AA Star, which we can give you a comprehensive timeline for until we're able to operate the full baseline design. And just noting that the subarray capability will be there in AA Star, and I'll get to that in a moment. Now, there is an opportunity upcoming, and many of you will have seen this through the science working groups. In June next year, there will be a conference in Görlitz, Germany. And to that end, we're putting together and updating, refreshing the science cases. So the current science working group chairs for gravitational wave astronomy with the SKA are, I've written here, Nicola Bellamo, Samaya Nisanke, and Alvise Raccanelli. And the 2 project scientist liaisons, Anna Bernaldi and Philippa Hartley. So please, if you have any question about it, reach out to the chairs, the project scientists, or me, or any SK person here at the conference. We do think, well, we anticipate, although we welcome feedback for the science case, but that timing activities will probably predominantly use the SK mid bands 1 and 2. This is just showing the timeline there with those particular bands shown down the bottom, and also showing the number of dishes in total. But I think for pulsar timing, it's probably the number of dishes in the core. That's the salient detail there. So AA2, there'll be 47, around the same sensitivity as Meerkat. AA Star, there'll be 100, and that's where things get interesting. This will, of course, be supported by SKA Low in terms of following DM and RM variations, dispersion measure and rotation measure variations of the pulsars. And there's 2 key modes that are being developed, which I don't have time to go into in great detail, but the pulsar search mode and pulsar timing mode. And both of these modes will support multiple beams and multiple subarrays, and of course will be informed by the Meerkat timing and search programs. So I think it's safe to say that the programs are probably similar to Meerkat, but with a more sensitive telescope and hopefully advanced capabilities. An important part of this is the ability to form subarrays, meaning that you can take the telescope and carve it up into separate, essentially completely independent telescopes. And so that means you can observe multiple pulsars at once, meaning you can get through your timing a lot quicker. Now, toward actually writing proposals and using the telescope, the science operations team, with a lot of help, has been putting together a series of user tools. And I just wanted to take you through those quickly. If you follow the QR code, it may be a bit cut off, so come and talk to me if not. There's extensive documentation and on these things that you see on the screen here. So sensitivity calculator, the stage delivery documents up there, which gives all the details that I just went through, so you can get that easily. And also something called the templates library, which I'll get into. Now, all of this is, we welcome feedback and we need the feedback. So please, if you have feedback, get in touch. Thanks. So firstly, there's the sensitivity calculator. We've recently added, you'll see here, a pulsar search mode, which will give you the sensitivity you would expect for a pulsar, depending on its various parameters. The other thing I've mentioned is this subarray template. So the SKA telescopes will be able to create up to 16 independent subarrays. And to do that, when you divide it, you could divide it in any way you like, but we've come up with 26 templates based on feedback from the science working groups. And I'll just show you some, for example. So this is an example where we're dividing the telescope, dividing the entire array into lots of similar subarrays where the point spread function and the UV coverage would be about the same for all of these. And this is just a method, so when you do your observations, you can observe quicker in particular science cases. Again, feedback is welcome. So we need to make sure that we are servicing the community and doing what is the optimal for the science cases. So please get in touch with us. Finally, I'd like to mention some recruitment opportunities. I am part of a large team, and the SK telescope itself is a huge team. There's job opportunities within the telescope and within CIRAO and CIRO and with the SRC networks and many other jobs. And we're just within the science operations team going to be building to a team of over 50. Currently, we have 12 roles open. These are all continuing roles. So 7 of these are based in Cape Town here, 2 at HQ and 3 are in Perth. And please reach out to me or someone else if you have any questions about these. But yeah, we'll be expanding rapidly, and we need good people. So please share this with your ECRs, your networks, and yeah. Finally, I'd like to mention that there is tomorrow an SKA day going from 10:30 a.m. to 5:15 p.m. To get there, it's actually across the Sky Bridge. And that's if you go out this door and then cross, you'll get to it there. But I'll just leave it there and say thank you very much.
Okay, thanks for the talk. Do we have any questions for Denny?
Yeah, Danny, I was wondering about the pulsar search mode, and particularly for big surveys. Is there going to be some kind of observatory-wide key science project that does a big survey, or will this be kind of PI-led surveys? Has there been any thought to how a major survey like that would be done?
There will be key science projects, and I imagine that this will very likely become a key science project. But again, will be informed by the science working groups, and the key science project will be made from there. And then there'll be a fraction of time which is for competitive projects as well. So we'll be doing both. But for large key science, yes, we'll have allocated time for that.
Thank you, Danny, for the overview. On the mid-array, you said that it's going to go up to 15 gigahertz, but it could go higher. What's the highest frequency it could go to?
I believe the dishes should be good. I don't think we've done all the verification tests, but spec'd up to around 25, 26 gigahertz. It'd be good to get to some of the spectral lines up at particular frequencies, but we don't really know the performance up there. There is also a band 6 receiver designed, but it's just in terms of cost, we're trying to build the optimal thing and try and get the maximum science with the currently allocated funds. So something that could happen in the future, and I certainly hope it does.
Okay, let's thank Danny again. And next up, we've got Maura McLaughlin. So if we could have the slides up.
Is this working? Great. Yeah, so I am not Scott Ransom. We switched the order of our talks because I was going to give more of an introduction, current results and implications, and Scott was going to talk more about the future. So we thought it would make more sense for me to go first. In a completely uncharacteristic move, I changed a slide at the last minute, so they're just uploading the new version of the talk. Yeah, so I'm going to be talking about the results of NanoGrav. As you might know, NanoGrav stands for the North American Nanohertz Observatory for Gravitational Waves. And we are a collaboration of over 200 students and scientists. We're funded by the NSF, the National Science Foundation in the US, as a physics frontier center. Most of us are located at institutions in North America, but we have members all around the globe. I'm also a member, as are many people in this room, of the International Pulsar Timing Array Collaboration. So this is a collaboration of 4 regional collaborations in North America, Europe, Australia, and India, and very soon South Africa, which is really exciting. And our goal is to combine data from all of these regional collaborations to form a very sensitive pulsar timing data set to detect low-frequency gravitational waves and characterize the low-frequency gravitational wave universe. We have some funding from the National Science Foundation, which supports IPTA cyber infrastructure and meetings, and it is partially supporting a meeting in June 2025 in Pasadena. So if you like what you hear in these talks, please come to that meeting. Okay. So thank you, Ryan, for giving an excellent plenary and introduction to pulsar timing. I'm not going to go into a lot of details about how it all works. I'm going to be describing the results of our 15-year data set. And this data set includes actually almost 16 years of data on 67 millisecond pulsars. Those pulsars are observed with the Green Bank Telescope in West Virginia, Arecibo in Puerto Rico, and the Very Large Array in New Mexico. And this little graphic here shows year. This axis are pulsars, and you can see how the array has grown from our 5-year data set to our most recent 15-year data set. And as you know, I know you've all seen plots like this. You're probably tired of looking at plots like this by this point in the conference. But the goal of our experiment is to search for spatially correlated perturbations in the arrival times of pulsars from this network distributed across the sky. And we're looking for this very special correlation that is a quadrupolar correlation predicted by Einstein's theory of general relativity. And the basic idea, of course, is that pulsars in the same direction will show correlated perturbations in their arrival times. Pulsars separated by 90 degrees are going to show anti-correlated perturbations, and pulsars at 180 degrees will again show correlations in their times of arrival. So this is this Hellings-Downs curve that we've been searching for, and other PTAs have also been searching for close to 20 years now. And these points here are the binned correlations that we see in our 15-year data set. Of course, when we do this analysis, we look at all the pairs of all the pulsars, every 67, all 67 pulsars with every other pulsar. But these are binned into 15 bins just for, ease of viewing. But you can clearly see the correlations dip at 90, rise at 0, and 180. So we were very excited when we saw this in our data a few years ago. Okay, so I want to talk today not so much about how we do the timing experiment, but what the implications are, and also a little bit about the significance, how we're sure that this is really a gravitational wave background and not something else. So this this is like an old version of the talk. Is there any way to upload the new version that's version 4, if possible? I'll just go on in case there's not a way to fix it. But so is there a way to get the newest version up by chance? Okay. Okay. Oh, there it is. Perfect. Okay. So these are examples of gravitational, this is what we search for gravitational wave signals. These are pulsar timing residuals. So these are examples from the 15-year data set. These are 3 different pulsars, and the residuals that we analyzed to search for this stochastic background of gravitational waves are the differences between model times of arrival and measured times of arrival. Right, and this model will include all the astrophysical stuff that we know is happening at the pulsar, the period, the spin down, binary parameters due to delays through the interstellar medium. And then we analyze these residuals to see if there is an unmodeled component to the residuals that might be due to gravitational waves, right? And you can look at these, you can look at the y-axis and see this is this 1 microsecond here, right? So we're doing pretty well. The root mean square of the residuals in this data set range from about 60 nanoseconds to 1.5 microseconds. But you also see some perturbations here, maybe some hints of noise in the data. We can't tell from looking at any one pulsar whether these might be gravitational waves or anything else. And so what we do is a noise analysis that looks something like this. So for this particular pulsar, we basically Fourier transform those residuals. We look at them in the frequency domain, and we calculate the spectral density over a range of frequencies. So this is at 1 over our time span, 2 over, etc. And then we model that with various contributions to this noise. One of those contributions is white noise, and you can see that gray line here. And then we have 2 what we call red noise contributions. So red noise that has more power at lower frequencies. One of those is intrinsic to each individual pulsar. So for each pulsar, it can have a different amplitude and spectral index. And one is a common source of red noise. And you can see that line right here. And that must have the same amplitude and spectral index in every single pulsar in the array. Okay, so for this particular pulsar, this is one of our best ones. So it has very small individual red noise. And most of the noise that we see in its spectrum, most of this low frequency power is due to this common red noise source. Here's an example that kind of goes the other way. This pulsar has more intrinsic or individual red noise than this common red noise. And we think this individual red noise is mostly due to intrinsic pulsar spin noise, and there may be some other contributing factors as well. Okay, so we do that exercise, and when we do that exercise for the data in this 15-year data set, we cannot model that data at all without this common noise process. This common noise process is strongly preferred to independent red noise in the individual pulsars by a base factor of about 10 to the 12 or so. So our model strongly prefers this common source of noise. It's not dipolar, it's not monopolar. There's very good evidence with a base factor ranging from like 200 to 1,000 that it shows these Hellings and Downs correlations that are predicted by general relativity. There is not good evidence for additional dipolar, monopolar stuff like sine waves in the data. So with the sensitivity that we have now, this Hellings and Downs correlated spectrum is the best model for this data. So this is really exciting. We take it a little bit farther. We want to know, what's the significance of this result? And the way that we do that is that we look at the Fourier components of this common noise and we put phase shifts in. So we insert phase shifts. We do this analysis over and over again with this phase shifted data. And that will preserve the characteristics of the noise, but it'll get rid of those spatial correlations, right? And then we ask, and how many of these phase-shifted versions of the data set do we detect something with a similar significance or signal to noise as in our real data, right? And we do that in a couple of different ways, kind of a Bayesian framework and a frequentist framework. And this gives us a detection significance of something like 3.5 to 4 sigma. Okay. these are just some interesting plots, I think, just to show kind of like the process that we went through to convince ourselves that this was a real signal. It behaves as expected. As we add more pulsars with longer and longer baselines, the signal to noise grows as we expect. If we break the data set into Arecibo and GBT only data, we get very similar spectral characteristics. This is the amplitude of this common noise process, and this is the spectral index. Okay. And of course, the real smoking gun for the astrophysical interpretation of the signal is that very similar things have been seen in the data from other pulsar timing array experiments, including the most recent Meerkat PTA results, which were just presented a couple of days ago, which is really exciting. So all of these different PTAs, a European and Indian PTA combination, Nanograv, the Parkes pulsar timing array, the Australian collaboration, they all have consistent amplitudes and spectral indices for their data sets. And oh boy, okay, I'm going to go faster. Okay, so, and this is just to illustrate that there are some pulsars in common between these different data sets, but some are not, and the telescopes are completely independent. So they're kind of like quasi-independent analyses, really. Okay, so why are we doing this? Why is this interesting? We think the most likely source for this gravitational wave background in our frequency band are supermassive black hole binaries at the cores of galaxy mergers, right? So we think that galaxies have grown larger and more structured through cosmic time, through the merger of smaller galaxies to form bigger and bigger galaxies. We see lots of evidence for this electromagnetically, but there's a lot of questions about how black holes at the cores of these galaxies get close enough for gravitational waves to be able to drive them to their final merger to a single black hole. And we think things like stellar scattering or maybe an accretion disk are responsible for, pulling angular momentum from the system so these black holes can get to those very close separations necessary. But we don't really understand the timescales involved. We don't understand the interplay between these different processes. We don't know if all black holes will actually eventually reach that final stage of merging into a single black hole. Some of them may get stalled. And so this experiment will allow us to explore this, right? So, and the way we do this is by looking at the spectrum. So this plot here shows the spectrum of this common noise process in our 15-year data set. These gray bands are the spectral posteriors. This blue line here and this band here, this is the best fit to our spectral posteriors. And this dotted line here is what we expect for a population of supermassive black hole binaries purely driven by gravitational waves, right? So this is a red spectrum. Even though this strain is higher at high frequencies for one individual supermassive black hole binary, they spend a lot more time in this part of this spectrum. So when you integrate over this, you get a quite steep expected spectral index of 13/3. And so you can see that our result is consistent-ish with this expectation under this very simplistic assumption, but it's a little bit shallower. And this is expected. If there are interactions between supermassive black hole binaries and their environments, we would expect it to take power from this end of the spectrum and eventually see a turnover. So this is expected, and this is interesting because it shows that there's astrophysics in our data. It's also consistent with other things. So I think our new physics paper is our second most cited paper out of all the papers that we published on this data set, because there are a host of other exotic explanations that are also consistent with this data. So things like inflationary gravitational waves, phase transitions in the early universe, cosmic strings, domain walls. And if you look at this, this is the base factor for this new physics explanation over the supermassive black hole binary interpretation. And naively, when you look at this, you think, oh my gosh, it's not supermassive black hole binaries. It's something really weird. This is just new physics. This is new physics plus a supermassive black hole binary. But you should take this with a lot of caution, because the supermassive black hole binary model that was used to make this comparison is a very simplistic one, circular orbits, gravitational wave driven. So you shouldn't walk away thinking it's not supermassive black hole binaries. You should walk away thinking it could be one of these other things. And we need more accurate models for supermassive black hole binary populations to really understand what these base factors actually are. But it's intriguing. Okay, and I know I'm running out of time. I'm just going to go through this really quickly. So if we want to say things about supermassive black hole binaries, what we do is we make fake populations of supermassive black hole binaries, look at the stochastic background that they generate, compare it to our stochastic background, and then use that to make inferences about the properties of our stochastic background. And when we do that, we can tell that our background is produced from high mass binaries. This solid line is the gravitational wave background fraction from different binaries with different properties. So very high mass binaries, roughly equal mass ratios. This final redshift is when they are close to merger, so close to when we detect them. This sort of at redshifts of 1 and some population of much closer binaries. We need very high masses. These are all the mass ranges that have been predicted from various astrophysical models. And here's our measurement. So we're sort of at the upper limit of the mass range. I won't talk about this plot right now. And I'll just finish by saying we also look for single supermassive black hole binary sources or continuous waves in our data. And this plot shows our limits in units of megaparsecs for a billion solar mass binary. At our most sensitive gravitational wave frequency, the red stars are pulsars. And you can see these squares here are possible supermassive black hole binaries. Actually, the diamonds are. The squares are galaxy clusters. We have very anisotropic sensitivity, but we can look out to sort of like almost a couple hundred megaparsecs. This is very sensitive to the presence of individual pulsars, the presence of the background. And I will just stop here. I'll just say, if we search at specific frequencies, we see some features in our data, like here and here, but this one goes away when we include the presence of Hellings and Downs correlations, and this one we think is due to a weird pulsar. And I'll just step through this. I'll just end by saying there's really exciting stuff coming down the pipeline when we start using electromagnetic observations of supermassive black hole binaries as priors for our gravitational wave searches. This has been done for 3C66b, and our current constraints are really close to the electromagnetic inferred mass, that we may be very close to detecting this one if the electromagnetic model is correct, which is really up in the air. But I'll just leave this pretty picture up. Multi-messenger astrophysics, that's the next big thing, and we're really excited. And I'm sorry for rushing a little bit.
Thank you very much. Yeah, thank you very much for going through all these wonderful results from Nanograph. And we have one question up here.
Thank you for a very nice talk. I was wondering about the model for the supermassive black holes.
Yeah.
Effectively, how many mergers do you need to use in this model, and to what extent are you limited by whatever is the nearest one in terms of? I'm just trying to get a feeling what the uncertainty is just from model to model. Limitation.
Yeah, so these models aren't empirical. They're not based on exactly observed galaxies. They're based on simulations, like the illustrious simulation, which just have some distribution of matter in the universe. But the models are dominated by tens, like to 100 supermassive black hole binaries, not thousands or millions.
Are there any other questions? Okay, maybe we'll take one from Peter while Scott comes up, and we can get the slides up from Scott as well at the same time.
So when explaining the Bayes factors for the new physics comparisons, you talk about how that's for a simple SMVH model. So how much power is there at this point for comparing, more realistic models and distinguishing among more realistic models for like other evolution factors besides gravitational wave emission and things like that? So are there firm conclusions being drawn with that, or is it still marginal with it?
Yeah, I mean, a lot of power actually. So in our astrophysics paper, we show that the data already prefer like a non-purely gravitational wave driven model, but there are still such huge error bars that I think for the purposes of this new physics paper, they're just sticking to this like one very simple thing. And I think the reason they haven't done more is that there are still just really huge uncertainties. And our next data set, like in our 20-ish so data set, we'll be able to constrain the spectrum much, much better. And that's going to help a lot. So I think in our next data set, if there's another new physics paper, it for sure will use a much more accurate astrophysical model.
Okay. Thank you, Maura.
All right. Well, hi, everyone. It's a pleasure to be here and speak after Maura, who really nicely summarized the Nanograv results as well as the IPTA results that came out last year. So I'm going to take over from there and talk about what's going to happen in the future, and especially a new observatory that's very likely to happen that Nanograv is going to be leaning on very, very hard in the future. So let's see if we're going to go. There we go. So here's the results at the top that Mari just mentioned. And I'm going to want to highlight at the top. Once again, this is the IPTA. All the different individual PTAs have basically seen the same thing over the last year. That's highly reassuring, including the new Meerkat results that were just announced recently also by Ryan. But what we want to know is if we're going to assume that this is really the gravitational wave background, what is causing this? Is it black holes, which we think is likely to be probably via Occam's razor, the most likely source? We know that they're out there and that galaxies merge. Or is it potentially something like something new physicsy that Mara also mentioned, related to early universe, distant universe, stuff like that? The next decade is really about figuring that out. So that's really what my talk is about. One of the best ways to tell the difference is via anisotropy. And this is going to happen just by the nature of the way the pulsar timing experiments work over the next decade. As we measure that gravitational wave background much, much better, we're going to be able to figure out what it looks like on the sky. And to zeroth order, if it's one of those new physics types of reasons why we're seeing a background, it should look isotropic. If, on the other hand, it's due to supermassive black hole binaries, just because of the way that galaxies are around, and we're going to be more sensitive to the nearby sources, we're going to see basically point sources on the sky, which is going to show up as lots of anisotropy. The current data to about plus or minus 20% looks isotropic. That is not a problem right now whatsoever. Whoops. That is not a problem right now at all for the supermassive black hole binaries. So right now, things are consistent with either the cosmological type models or supermassive black hole binaries. But this is where we're going to go. So how do we do this? How are we going to move forward? What is the way to do that? So it's based on the way that we do these observations. So here's very quickly what we have been doing in the past. The Nanograv observations have hugely leaned on Arecibo and Green Bank, basically split 50-50. About half of our sensitivity came from each of those telescopes, with a little bit of extra data coming from the Very Large Array in CHIME. But the big problem is that Arecibo has collapsed a few years ago, as you know, which was a huge hit to astronomy in general and a very big hit to pulsar astronomy and Nanograv. So what's happened is we've basically switched to covering almost all of our pulsars with the GBT, which is less sensitive. And we've also had to shrink the amount of time that we're spending on each pulsar. So we've leaned very heavily on CHIME for those other observations. This is what our data set looks like. These are the 15 years, and every column is basically a different pulsar. These boxes show the data releases that we've had over the course of the years and that we've published. So this is our 15-year data set that we just published. And notice the trend here. We're continuing to time pulsars, and we're adding pulsars to the array. And that's really important because this is how we go to much, much better measure the gravitational wave background and figure out if there's anisotropy and single sources in the future. And these scaling relations are part of that. So the biggest thing to notice is that the gravitational wave sensitivity is directly proportional to the number of pulsars that are in the array. And that's related to the Hellings and Downs curve, which has got an n-squared relation because it's a pairwise cross-correlation statistic. So it goes as n squared. So the sensitivity is related to the number of pulsars, square root of the number of time, the amount of time that we're timing things, and also related to the noise properties of every pulsar. So the best pulsars do a little bit better for us than the worst pulsars. But the most important thing that we want to do is add pulsars. That's the name of the game. And this is where we're going to be going in the next 10 years. Right now, we're already timing all of the best pulsars that we possibly can with these PTAs. That's important to know. So then we're currently working on our 20-year release. So we already have this data all in the can. I mean, this is all available right now, and we are working on this 20-year data set. That helps us also, besides the square root of time increase, in the fact that as we go to these longer time spans, we are automatically probing lower frequencies where the gravitational waves are stronger because they're steep spectrum sources. So that's where we are right now. We're working on that. And in the 10 years in the future, basically what we want to do is fill in this massive area here by lots of new surveys, pulsar surveys, to find hundreds and hundreds more millisecond pulsars, and then choose the best ones to time with the next generation very large telescopes. And the one I'm going to be focusing on in the rest of the talk is the DSA 2000. This is an artist's concept of what that's going to look like. We'll talk about that. But all of these new modern telescopes, Meerkat's already doing a fantastic job, FAST in China. They've already found hundreds of new pulsars with each of these telescopes. And then the SKA and DSA 2000 are going to find tens of thousands of new pulsars. This is where we're going to expand this array. And with that incredible sensitivity to the background, we'll be able to figure out what's going on with the anisotropy. And we think with the DSA 2000, we will be timing something like 150 to 200 millisecond pulsars with the DSA 2000 plus GBT. And if you think about the IPTA with SKA mid, between 200 to 300 pulsars in total. All right, so what is this DSA 2000? Well, it's 2,000 5-meter dishes. This is not yet funded, although things are looking pretty good, so cross your fingers. It will be built in Nevada on a very ambitious timescale. Incredibly sensitive. These are very simple dishes with a very straightforward mission for this telescope. It's doing all sorts of gravitational wave follow-up, radio transients, a radio survey of the whole sky on multi-epochs, and 25% of the time goes to nanograv. That's the really big thing for nanograv. All of the data will be fully open, and this is pretty crazy. First light potentially as early as the end of 2026. And that may sound absolutely impossible, but it's actually might happen. It's astonishing. Things always get delayed, so we'll see. But it's an incredibly interesting facility. This shows how things are working for nanograv with our observations in the past. Arecibo and GBT, this was how we were ramping up those pulsars. Then Arecibo collapsed. This is where we are now. Basically 2026 or 2027, the DSA 2000 is immediately going to start finding new pulsars. And so we're going to ramp up and be observing a huge amount of time on all these new pulsars from day one with the DSA 2000. It's one of the earliest science projects with the DSA. So what's going on with the development of this system right now? Here's the first dish. This is not an artist's conception. That is actually the dish out and mounted and being tested. It's everything about this is incredibly low cost and to be made very easy to maintain and to build. So you can, this is a hydroformed vacuum forming system to make these dishes very, very cheaply. This feed right here is literally made by a cake pan manufacturer. It's called the cake tin feed, but it has incredible performance. It's not cryogenically cooled, but the system temperature is something like 25 Kelvin measured. This is not theoretical. This is measured on sky already. This exists. Here's the location in Nevada. It's a big, between two mountain ranges. There's basically 0 people who live anywhere near here. The interference is very, very low. There's almost no cell phone coverage. It's really an amazing site. Here's what the pattern on the ground is going to be like. It's a little bit more north-south than east-west. This is roughly 15 kilometers by roughly 20 kilometers. And all of those dishes go in that very, very small area in order to do the radio survey, an imaging-based survey. But we care about it for the pulsar timing. And given this amount of sensitivity, this is basically, thank you, basically a fully steerable Arecibo that has 25% of its time dedicated to nanograv. So this replaces the sensitivity that we lost in Arecibo and allows us to get a much bigger sky coverage to find and time more pulsars. This is one of the most interesting things we're potentially going to be able to do with this new facility and with this expanded number of pulsars. Once we nail down that anisotropy, and if, assuming this is black holes, we are going to see within the next 10 years, well, let's say the next 15 years, potentially dozens of individual sources. This diagram right here shows the predictions with the nanograv data continuing, and then 10 years, so basically starting at the end of 2026 of DSA 2000, here's our sensitivity with that new data set. And these blue curves are 95% conservative upper limits to where we'd see 1, 2, 3, or 4 detectable binaries. And you notice that we're well underneath there. So in a plausible situation, if what we see with the background really is due to supermassive black hole binaries, we should see tens of individual sources by mid next decade. And given that LISA is going to be coming online potentially at the end of the next decade also, we have Cosmic Explorer and the Einstein telescope. Really, really interesting decade for gravitational waves next decade. And the PTAs are going to be right there. The last thing I want to mention is that with this massive new sensitivity, with both SKA mid and DSA 2000, provides a revolution in things you can do with pulsars. So for instance, this is the observation that led to the 2 solar mass neutron star, the first of the 2 solar mass neutron star papers. The single observation, because we used a new instrument, this was a factor of 3 times more sensitive than previous observations. So it's similar to moving from, say, the GBT to Arecibo or GBT to DSA 2000. We instantly were able to get a measurement that we were not able to do before. And this is the type of thing we'll be able to do with all of these thousands of new pulsars. So there's going to be a lot of really exciting pulsar science with both SKA mid and the DSA 2000 in the next decade. And I'll end right here with this future. Immediately, we have a new ultra-wideband with GBT. Within the next year, the 3rd data release of the IPTA data. So you'll see all that in about a year from now. The DSA 2000 is very likely to come, and the next decade is going to look great with propulsar timing arrays. And hopefully we'll make this red curve, which is now pessimistic because of Arecibo, launch straight up just like the Meerkat curve. And I'll end there. Thank you.
Thank you. Do we have any questions for Scott? I was curious to hear a bit more about pulsar searching on DSA 2000 and what the strategy and plans are for that.
Yeah, so it's also very ambitious. So there's going to be something like 400 beams, tide array beams that are created every time there's a survey pointing to do the radio camera survey of the whole sky. Those beams in a real-time pipeline are going to be GPU processed and searched, including with acceleration searches in real time. Well, it's pseudo real time. Like by the time you're doing one observation, it's searching the previous one. And right now, we think the computing exists. The basic algorithms and the code are roughly exist, but this is a very high priority, basically starting from day 1 of the DSA.
Impressive stuff. I was wondering, the spectrum you showed looked extremely clean, but from when is that? Because with mega constellations coming up and whatnot, that's going to get way worse, I think.
Yeah, that's definitely true. The mega constellations are gonna hurt, and the frequency range, as you can see here, the DSA band is basically from 700 megahertz to 2 gigahertz, and a lot of those mega constellations are in that band. So that is totally true. So far, there's a whole session, symposium here at this meeting about exactly this. There's a lot of great coordination that's going on with at least SpaceX right now, and we're hoping with the other major constellations to avoid major facilities. We don't know if that's going to work, but hopefully that will help. But this was taken just within the last year and a half. These RFI surveys of this valley.
Great, and we'll have one final question.
Yes, I was curious about the 15-year data set. You had a gap in there of many pulsars. What's the cause of that? Between 2017.
Yeah, right here.
Yep.
Yeah, so this is from the Arecibo data. We lost a year of data because it turned out a local oscillator at Arecibo was unstable at a very low level that we could not easily tell when we just took the data. It looked completely fine. But when we did the precision analysis of those data, we found that it was unstable and we had to throw those data away. Yep.
Okay, let's thank Scott and all the speakers for the session again. And I'll hand over to Paul.
Thank you. We're at the end of the symposium. Thank you, Scott. We're at the end of the symposium, so I would like to say a few closing words on behalf of the Scientific Organizing Committee. It's been a roller coaster the last 3 days. And it's fantastic to see so many new ideas and so many new results coming out. When we put in the proposal for this symposium to the IAU about 2 years ago, we thought this whole symposium would be dominated by mostly LIGO Virgo, GAGRA, ground-based results, and also the electromagnetic ones. The fact that we're still waiting for a good neutron-star merger in 2004 is sort of a blessing in disguise, I would say, because it gave us the opportunity to show the richness of gravitational wave astrophysics in its full entirety, and actually give the floor also to the pulsar timing array results, to the LISA results, to the future, and it really shows that this is a field that is coming into its own. This GA is a GA first. It's the first in Africa. It's the first, therefore, also in South Africa, but it is also the first gravitational wave astrophysics symposium ever on a General Assembly. And I think it will definitely not be the last. I'm already looking forward to the future ones. So where do we go from this? One thing for the speakers, you will be contacted, you have been contacted by David Buckley, one of the SOC members who is also chairing the proceedings. And we expect your proceeding contribution by October 15. So this is just to the speakers. Also, the next step is next Wednesday. There is the meeting that Samaya and Varun are organizing on the multi-messenger side, which of course is almost synonymous to gravitational wave astrophysics. So those are the immediate steps. And I would like to thank a number of people, especially my fellow SOC members. Some of them are here, Marissa, Samaya, David, but especially also Ilya, who has taken up a lot of the slack in the organization. So I would like to thank all of the SOC members. Of course, the IAU for allowing us to organize this symposium, but especially a very big applause to the NOC, the National Organizing Committee, that has been organizing all of the organization of the GA and has taken away so much from our hands as SOC and have been running this. And I hope that you will be able to stay for the next week as well and enjoy the richness of astronomy as it is displayed by this General Assembly. So I would like to also stop here and thank the NOC, the National Organizing Committee, for all the work that they've put in to make this such a fantastic meeting. And I would say, in closing words, as we say in South Africa, gravitational wave astrophysics is baie lekker. Thank you.